So as we're kind of like filtering in, you guys can like say hi or wave at me or whatever. There will be plenty of time for you to interact with me, but if you want to get started early, now's a good time while we're waiting for people to trickle in.
Hi, Cameron.
Hey, Alex, how's it going?
It's going okay. So, so Natalia is not going to be able to make it. So
Yeah.
I'm going to be the check questions in the chat.
Okay.
Yeah.
Okay, perfect. So if they come up, I mean, my preference is that people just kind of interrupt me.
Okay.
But if there are like little tiny things in there that you just be like, no, it's this, then by all means, go for it.
Sure.
And let me know whenever they come up as well, if they're like slightly more complicated than basic questions, so then I can just kind of like stop and handle them because I may not see the chat window. Okay. Let's see. I'm getting a lot of people come in. Okay. So I've kind of leveled out at 22. Does that seem about right? Okay. I think I'll probably just get started. And people can jump in when they need to. Okay. Hello, everyone. Lovely morning. I assume most people are on Pacific time. And if they're not, then they're missing out because it's like a lovely day outside. And I'm very happy to have such nice weather today. So my name is Cameron Pfeiffer, and you are in the Julia Bootcamp, Julia for Economists Bootcamp thing. This is the first session on basics. So I think kind of without further ado, I'm just going to launch into things. So let me get my slides up here. Okie dokie. All right. I'm going to presume everyone can see my slides. And if not, then, well, this will be a really unpleasant session, won't it? Okay. So my name is Cameron Pfeiffer. I'm a visiting PhD student in finance from the University of Oregon. But I'm really more of like a just general computer guy. So I work on like anything computational, basically. So I work on a lot of Bayesian methods and applied metrics and macroeconomics and stuff like that. So basically anything that's like computational, I find to be very interesting. But nominally, I'm in finance. And I'm here visiting thanks to Shoshana Wasserman, who is wonderful. You should work with her if you have the opportunity. Okay, so I wanted to like post it like up front, like what my credibility is, right? Because I'm like a PhD student. You may not care that much what I have to say, but when it comes to Julia, I think it's like kind of one of my more outstanding skills. So I've been a core developer for Turing, which is a very large package for doing Bayesian inference. In Julia and all of its satellite packages, because there are many, for about 4 years now. And so I've written a ton of Julia code. There's like not, like I started working on Julia like before Julia 1.0. Like I think I started writing in earnest in like Julia 0.4, which is a really bad version of the language. It's not it's not, it's a billion times better than it used to be. So I've been around for a long time and I've kind of gotten to watch Julia grow and become as cool and interesting as it is today. So I like to think I'm pretty good at writing, fast code that looks like the Julia code that the community tends to write, and that tends to be easily read. So, I like to think that I'm pretty okay at writing Julia code. So that's why you should believe me when I say anything, but you don't have to, that's up to you. So here's just some of the packages I work on. You can flick through this list if you recognize any of these. But basically, I work on Markov chain Monte Carlo methods and how to do them like quickly and easily so that you don't have to like tinker around and do all this like kind of really complicated, stupid stuff that you usually have to do with Markov chain Monte Carlo. And then I'm attached to like a whole bunch of like little private code bases for people's projects that I submit a lot of code to. And then I tend to bounce around the Julia ecosystem if there's like a bug that's getting in the way of various things. So I'm fairly prolific in the Julia open source community. Okie dokie. So this series was kind of like pitched as a way to get economists kind of up and running with Julia. and I kind of have a vested interest in making sure that, you know, people are a little bit better at writing like good code, because one, I really don't like hacking together people's like R, Stata, like SAS code that they've written together, and they're like using a different language. They like have this one script in Python that they didn't know how to write Python, so it's really complicated. So I kind of want people to be able to write better code, and I want them to like be expressed, be shown how it is that people who work computationally write code well. And so like that's kind of the intention for the series, is that I can show you how I think about writing code, and kind of how you can do it better if that's something you want to do. So today is Julia Basics. So this is like just about the syntax. It's like how to get stuff running. It's about just like the core component of the language. The future sessions are like way more interesting and way more technical. So it's going to be like there's parallelization. So if you want to work on distributed computing or multi-threading or whatever, or GPU stuff, I'll put a little bit of this in there, and it'll be a lot more technical and a lot more interesting and way more applied. Same thing for optimization and automatic differentiation, which is kind of one of Julia's big superpowers. If you're like a person who likes thinking about like computer science type topics, this performant programming and best practices thing is going to be your jam. So this is like all about like what the compiler is doing and like how to write fast code in Julia, like really fast code. And I'll talk a little bit about Git and how to be like a good co-author if you work with code and that kind of stuff. So this one's like for, you know, people who are collaborators who want to like really excel at computation. And then this is my favorite one. This is like the one that I work on a lot. So there will be a Bayesian inference thing, computational Bayesian inference, Markov chain Monte Carlo type stuff. So you can jump in at any or all of these. You know, if you like drop out through this session and like, you know, halfway through, that's totally fine. You can come to the other ones. Just, you know, I'm happy to accept all skill levels, and I will provide refreshers as needed if some of the topics seem a little technically complicated. So don't feel too bad about, you know, missing some of these or coming for the one that you're really interested in. They're all fine. Okay. All righty, let me put this over here. Okay, and if there's something you like really want to know how to do, like if you're working on like an applied problem that you like kind of don't know how to do, maybe you want to do it in Julia, or maybe you started doing it in Julia and you're not quite sure how to proceed, let me know, because I kind of like, you know, these are things that I think that people work on. Like it's not like a whole lot of stuff that I know people work on that I need, you know, that I can help you with. So if that's the case, please send me an email and we can be in touch, and either I can help you personally or I can put it in the content of the talks in case they're like super interesting. Okay. All righty. So each session is basically 4 hours. We go from 9 to 1 Pacific time. And I'm going to lecture on a specific topic for 10 to 15 minutes. And then I'm going to give you like some little practice tasks. And we're going to go into breakout rooms, and I'll flicker around and help people out with the practice tasks. And then I'll go over it in front of everybody, and I'll show you how I would do it. So during these like practice tasks, we're going to put you into breakout rooms, or you can select breakout rooms based on different levels of your interest, right? So a lot of people just like, maybe they're here because somebody was like, you should go to this. That's fine. Or maybe you're here because you're like super into it and you really want to know. So if you're like the kind of person who like wants to figure stuff out and wants to be right, go to the nerd room. So the nerd room is like where you can find all the other nerds who like want to work on stuff, and you guys can talk to each other and try and figure it out. If you're like a person who likes to tinker, but you don't necessarily care about being right, go to the Geek Room, right? So this is where if you just like kind of want to tool around with stuff, that's a good spot. And you can go to the dork room if you just like don't really, you know, if you just like want to take an extra break, or you have other stuff to do, or you have a phone call or whatever, you know, like you can just like go here and do kind of whatever you want. I don't mind. I'll show up in these rooms every once in a while. But you know, I can only help you if you've like actually done stuff or thought about doing stuff. And I can also help you get started if you want to. Okay. And at the end of the concept check, I'm going to give you like, I'll tell you how much time I'm going to give you for each concept check ahead of time. And then at the end, I'll bring everyone back to the main room and we'll go through the answer. Okay. And we're going to have a 10-minute break every hour at the top of the hour. So, you know, we'll have one from 10 to 10:10 and a 15-minute break Oh wait, is this 11? This should be 11, sorry. 15-minute break at 11. Okay, and at noon, we're basically going to transition to a different platform than Zoom called Remo, and that's going to be more like a hackathon style environment. So I'm going to give you a project, which is basically like a super simple OLS estimator that allows you to get spherical standard errors or bootstrap standard errors if you want. And you should be able to do that in about an hour. And I'll be like wandering around and writing my own version. And I'll be available to help people, through the project. Okay, so you don't have to stick around for that if you don't want to do the project, but I think it's a good way to kind of cement everything in your head. All right. House rules about Zoom. I was hoping this was going to be in person. It is not in person, which sucks because I'm a super interactive type person, especially when I'm teaching. So I like to be interrupted. That is my strong preference. So if I'm saying stuff and you have no idea what I'm talking about, you'd be like, man, what are you doing, man? You need to work on this. So please interrupt me if you get lost or you have a question. You just turn your mic on and start talking and I will stop. And
why do you like to be interrupted?
Why do I like to be interrupted? Is that what you said?
Yes.
I like to be interrupted just because I like to stop when the second you recognize that you're confused, because then I don't have to get too far from the point of confusion. And it's just a little easier for me to like remember what it was that I was just talking about when you stop me about it, because I think I very short attention span. But if you don't want to speak up or you can't, you're in a place, you're somewhere where you can't have your microphone on, something like that, you can put your questions in the chat. Alex is helping me out with the questions in the chat. So Alex can help with like super basic questions if they're in there, or he can just kick them over to me and read them to me or notify me that they're there. So I like to have interactive classes. So let's help me out here. I appreciate it if you're like, yeah, okay. Okay, stupid questions. I will be so mad if you say, maybe this is a stupid question. It is not. There has never been a stupid question about programming in the world, ever, in the history of time, because programming sucks. It's like the world's worst thing to learn, especially when it's like kind of a new language. And I'm here to make it palatable to you. So if you start to feel yourself getting off track and you're like, no, I shouldn't ask this, there's all these smart people in the room. No, absolutely not. Just ask me the question. Like, don't start it with maybe this is a stupid question. So best case scenario, you ask a question, everyone else is confused and you're the first one to ask. And that means you're brave. And asking the question solves a ton of problems. And I'm much happier because, everyone's smarter. And worst case scenario, you yourself become less confused, which is very important. You should ostensibly care much more about your own understanding than other people's understanding. And it'll also help other people concretize their understanding too. So they'll understand a little better if you ask your question. Okay. I'm going to apologize in advance because I'm a very excitable native English speaker. So I tend to speak really fast and I may use a lot of idioms and slang. And this can be really difficult to follow. If you're not a native English speaker, I have a Persian friend who says he learns from me all the time. So please let me know if I'm I'm getting into a mode where it's difficult to understand me. I'm happy to repeat stuff or like rephrase or things like that. Like I apologize, I'm working on it, but I'm excited, so I want to go fast. Okay, all right. So that's the like boring stuff out of the way. Now we're going to get into this is like the table of contents for the rest of the talk. So I'm going to talk about what Julia is at a high level, how to install it, how to write code in it. I'm going to go through all the syntax and like some of the basics, like the semantics of the language, some of the interesting stuff about it. And then I'm going to do like the super core stuff that you may need if you're working with data. So CSV and data frames is how like you typically read some kind of data into memory. Fixed effects models is kind of the like gold standard in Julia for doing, two-stage least squares, clustering, standard errors, that kind of stuff. Then I'll do some visualization stuff about like how to do plots. So these are like just like the really core basic stuff that you need to do some kind of data science stack type things. And I think we're probably going to end up scratching the maximum likelihood thing. I don't think we're going to make it. But I will defer that to the optimization session in case you're like super interested in how to do weirdo maximum likelihood routines. Okay. Any questions on this stuff, like things you expected to see here or wanted to know more about? Okay. Cool. Oh, I should have just gone to this slide. Okay. All right. Then I'm raring to go. I hope you're like raring to go too, because this will be fun. And I want to make you guys sick of me because I've got, what is it, 3 hours and 45 minutes to go. Yes. All righty.
Cameron,
Let's do it. Go for it.
Cameron, are you also speaking a little bit about the namespace management, or is that maybe too advanced? I mean, for today or in later classes?
I have a brief example about this, but I think for like basic purposes, I don't care so much about teaching people how to manage like modules and namespace stuff as well. Okay. But I'll show. I have like a little box of types that I'm going to show you how to like put stuff in modules, but nothing too formal because it's more of a performance thing and a scoping thing. But yeah, I will defer that to the best practices session.
Okay, thanks.
Good question. Okay, I am not a salesman. I am not like some kind of Julia salesman. I'm not here to tell you it's the best thing since sliced bread. I happen to love it, but it's a tool. There are a lot of languages to write code in, and many of you might be really good at a bunch of other languages, right? I suspect there's a lot of people in here who are like pretty good at R, pretty good at Python or SAS or whatever. And that's totally cool. And if those are great tools for you and you are very efficient in them, then kind of stick with that. Like part of the joy of learning a new language is like figuring out the quirks and stuff of, like a new tool. And maybe you enjoy learning that like I do. So just kind of be aware that what you're learning here is I'm giving you a new screwdriver today. It's, I'm not telling you, here's the best screwdriver. All the other screwdrivers you can set them on fire. We don't need them. So use what works. Especially when you're learning Julia, it's going to be kind of a pain in the ass to get stuff to work. So I'm not going to get into your like Stata R flame war thing because that's just a huge waste of time. But I do not like questions about Stata because Stata lies to you about everything. So ask me questions about Stata or try to make analogies to Stata at your own risk. So that's as far as I'm getting into the flame war. And use Julia when it's appropriate and when you want to work with it. In my case, I think I use it more than I should, just because I really like working in it. So, because R and Python and Stata or SAS are all very good at a lot of things. Okay. So this is the very high level version of what Julia is. So first, Julia is really easy to learn. Like, the stuff I'm going to teach you is like a little bit more advanced than what you need to know to write the language. But in general, you can write super easy code in Julia without thinking too hard about it. Like if you just kind of squint at the code, you can kind of understand it in almost the same way that you can kind of squint at Python code and understand it. Like one of the joys of Python is that it's very easy to read. And Julia has that same property where you can just kind of pick it up and go. And if you want it to get faster, or you want it to get smarter, then you can, start digging into the weeds. But you can step anywhere you want to in the learning curve. If you write it well, it's really fast. It's hilariously fast. Like it's not even fair how fast it is for this form of language to be as fast as Julia can be. So if you write really good Julia code, you get C level speed or Fortran level speed. Sometimes you can even get like bare metal assembly type speed. But it's still pretty fast if you just like don't care. So if you're just like kind of messing around, you can still get really fast code. You don't have, you're not going to get this like bare metal type speed, but it'll go really fast. And it's very forgiving that way. For those of you who are like kind of compiler people or like programming languages people, Julia is what is called just-in-time compiled. which is very different from the languages that you are probably used to so far. So if you work in R is what, or Python, or many other languages, those are what are called interpreted. And interpreted basically means I will think about what your code means when I get to it, and then I will forget about it after I run it. Just in time compiled basically means I'll get to your code, and then I think about what that exact code, like this function, means, and then I compile it into machine code, and then I save it so that when I go back to it, I have that machine code. So there's always this little lag at the beginning when it sees a new bit of code where it turns it into machine code. But after the second time and every other time after that, it runs way faster. Interpreted code, in R and many others, tends to be quite slow because it has to redo the machine code every single time, basically. It's not like, it's kind of like a high level description of what's happening. It's like pseudo wrong, but it's close enough. But there is an interpreter for Julia if you want to, if you really like interpreted Julia, which is kind of stupid in my opinion, but it's good for things like debugging. And there is also ahead of time compilation, which is what you might know of if you work in C++ or C or Rust or whatever. All of those are ahead of time compiled languages. And stop me if there's anything that you want to know more about in here too. Julia is dynamically typed, so you don't have to say the types of things ahead of time. And if you have like a new type that enters in the runtime, you can just get a new function. That's a lot of like technical stuff, but it's important and interesting. Very reproducible. Like, this is my favorite thing about Julia. Like, if I have stuff on like the ends, I have stuff on all these like random cluster computing things, I can just like drop ship Julia code and it just kind of works if you do the package management correctly, and it'll always work. It's very robust. Like, it's another kind of unsung feature of Julia. It's very composable. This is complicated, but basically, if you write packages A and B, in R or Stata or whatever, those packages can't really talk to each other very well. If you do things in Julia, you tend to have all these cases where packages A and B just can use each other for free. And you don't have to think about it. You don't have to write any of this code. It just kind of works. And it's really amazing. It's just like absolutely beautiful. Julia is also technically general purpose. So you could write web servers and stuff in it, really good web servers. But people don't tend to use it that way because it started out as a scientific computing project at MIT. And it's, much of the community is all scientific computing people. So there's a lot of like climate modelers and dynamic systems people and differential equations folks and some economists. It's actually quite a growing community. It's also open source. You can tinker around with it. You can change the code if you want to in Julia and most packages, basically. It's also a beautiful language. Like, visually, I find Julia to be like quite pretty looking, which I feel is a stupid thing to say about a language that you like. But it's important to me. It's kind of what sucked me in initially, and then I kind of grew to love the actual features that are not just how it looks. Okay. Any questions on any of these? Some of these are very technical. Some of these don't matter. For the most part, it's fast and easy to write. Okay. What Julia is not. So I wanted to add a little disclaimer here because I think I want to manage some people's expectations about what it is that you can do with Julia. And this list has been getting really short lately. If I wrote this maybe 2 years ago, this would be the whole slide, the whole page would just be things that are bad about Julia. But now it's basically just 2. So the first one is Julia, because it is just in time compiled, you have to wait a little bit when you first run your code because it's being exposed to all of this new code, and it has to compile everything that it sees that you're using. And so there's this problem that's called time to first plot in Julia, which has been getting significantly shorter. But if you start up a new Julia session and you say, I would like to plot a straight line, sometimes that can take you several seconds. And that feels really awful to a lot of people. In R and Python, it just pops up because, you know, it's interpreted, it doesn't care, it's not trying to save that machine code, it just is. It just generates the plot for you. And if you're looking for things that are like canned, ultra robust, hyper advanced kind of classical statistical tools, those are kind of hard to find here. So if you're working in stuff like, if you're doing stuff that's like IV and clustering, all those things are things you can do. But if you're doing like some crazy GMM type thing and two-stage least squares and blah, 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 it's not like a one-line call like it is in Stata or, you know, R with a little bit of work. You kind of have to roll your own if you're doing stuff like this in Julia. And the robustness stuff, which is kind of a, you know, there's a reason that that people still buy SaaS licenses, because they indemnify you in court. If somebody challenges your analysis in SaaS, like they'll send lawyers. They'll send lawyers and say, no, it's absolutely correct. Or if it came through SaaS, the stats are right. So if this is a need that you have, if this is something that you need, if you need some weird statistical procedure, you know, reach out to me and I'll see like what we can do, or I can point you to something that already exists at kind of a lesser extent, and maybe we can like improve it and make it slightly better. Okay, any other questions about this kind of stuff? What it is and what isn't? Okay. Okay. Hold on, I'm going to drink my water out of my incredibly bright bottle. Okie dokie. So I'm going to show you some like just like flashy stuff that you can do in Julia, and some not so flashy stuff, but you know, common things that you might do, or cool things that you might do because you're feeling like saucy. Okay. So I'm basically going to show you how to like test like a bunch of specifications of something and get like a nice little regression table output. So this is going to use the iris data set, which everybody is familiar with, I assume. I'm loading a couple packages. Fixed effects models here is the one that allows me to do these regressions here. Our data sets gives me this data set function. I'm converting the species to a string, a categorical variable in this case, and then I'm adding various fixed effects. And you can add clustering here too if you wanted to. I haven't in here, but I can just create a little regression table with my estimates for a different y variable here. You'll note that it's simple with. And you'll note if you work in R, this is designed to be similar to the R style formula that you find, right? So you just specify y variable, a tilde, and then your regressors here. Okay, so this is just like kind of nice and quick. It went really fast. And by the way, when you see things run really fast on my machine, it's because I ran all of this code beforehand. So everything is already compiled. So we don't have to like sit and wait and watch. You know,
hey, Cameron.
Yes.
Cameron, quick question. What does the exclamation mark in the third line in the data frame do?
So the exclamation point means modify. So basically this says take all of the rows in data frame in the column species dummy and change them to whatever is on the right. So the alternative in data frames is this. So if you put a colon there, that means I want to look but not mutate. So I'll talk a little bit more about this. You can use the exclamation point basically everywhere you want. But you know, if you only here, so here would be here's the idiomatically correct way to do this, where you note I have a colon on the right-hand side, which means look into this data frame and all the rows of this column. I'm not going to change anything that's in there. I'm going to basically make a copy of them, convert them all to strings, and then put them back into the species dummy column by modifying this whole column or creating a new one.
Thanks.
Yep. Okay. All right. So that's kind of just like regression stuff. If you want to do like Bayesian stuff, which is my thing that I love, I'll give you I took the same data. So I took the flowers data frame that we have. I'm using Turing here, which is the package I work a lot on. I'm defining a probabilistic model here. I put this at model macro here. I'll talk a lot more about macros during the like performant Julia best practices type thing. And all of this function does is it accepts some data about flowers, this iris data set. I'm defining an intercept here, and I'm defining a coefficient, and these are the priors. So I'm saying alpha has a prior of normal prior with a mean of 4, variance of 1. Same thing for beta, but the mean is 0. And then I have a sigma squared here, inverse gamma. And then I'm just going to say, well, all the sepal length data, which is my y variable, I'm going to calculate basically the likelihood of observing those sepal lengths with intercept plus beta, which is my coefficient on sepal width, with a homoscedastic variance here. So it's just sigma squared times the identity matrix. Okay, and then I'm going to create the model here, and then I'm just going to sample it. So in this case, I'm going to sample 4 chains with 2,000 samples per chain. And if you're like a person who knows about Markov chain Monte Carlo, I am using NUTS. So NUTS is the no U-turn sampler. So here are the point estimates for my posterior distributions for alpha, beta, and S sigma squared. So here I'm finding that the mean in this particular very small model is 6. And I have quantiles and stuff for free. And I can also just plot the densities if I want to. So this is a common thing that you find in Bayesian methods as well. So that was nice and quick, super easy.
So was that the normal speed, or is that, are we time to first plot here?
Turing is pretty good at getting around the time to first plot. Actually, the biggest thing is showing the biggest computational cost for like doing a new thing is making this table here. Like it takes a surprisingly long time to actually print this out to the screen. But Turing is written in such a way that, you know, you do one sample, which maybe takes you a quarter of a second. And then the other ones are all compiled. So Turing is much, much quicker. This one here, that, you know, you're not going to see the time to first plot, but at least for here, it doesn't matter quite so much. Let's see. And then who here works with like differential equations? I imagine there's like a couple of people that do. If you're like working like auction type stuff. This is a perhaps little known fact, but Julia is the home of the world's greatest differential equation solver. So there's this guy at MIT named, he's now at MIT, I guess, or no, maybe he left for just Julia computing. But he basically spent a ridiculous amount of time building this massive network of tools to solve differential equations. So every solver that's ever been in a paper since like 1941 is implemented in a really fast way. Like it kicks the ass of everything that's in MATLAB. Any possible differential equation solver you can find, they're beating it by like orders of magnitude in terms of speed. So if you work with differential equations, you should probably be doing it in Julia if you care about speed and correctness. And once you throw automatic differentiation into the mix, you just like get all this crazy stuff for free. So here's just like Lorentz equations. I don't understand this. I never learned differential equations correctly. So maybe you can use that to take take all of my claims about differential equations with a little grain of salt. But here I'm just defining the actual differential equation system. I'm giving it some initial conditions. I'm telling it, saying, you know, how long do I want this differential system to run, differential equation system to run? I define a problem, which is the, you know, given by the Lorentz function, the initial conditions and the time span, and then I just solve it. And it picks a solver for me. It tests basically the stiffness of you, or, you know, your basically the properties of your equation. It'll give it a test and try to figure out what the best solver is. And there are many. And then I can just plot it, and I get this nice little 3D plot with the Lorentz attractors, which are very pretty. I'm not sure what they're used for, but it's pretty. Okay, so questions about just kind of like the differential equations, like little thing here. We'll talk more about this in probably the optimization thing, because I think it's important. But yeah, just wanted to show you cool stuff. Okie dokie. Any questions before I move on past the demo? We're going to get into like actually making sure you guys can follow along now. Okay, I have a poll on. I want to know what people's operating systems are. Riley, could you put up the little operating system poll? Thank you, thank you. Okay, so.
Quick question, Cameron. For this
Yes.
tutorial, can we do it on the yens maybe? Is that an option?
Yes, you can do it on the ends if you prefer. Alex is here. I don't know how much he cares about having the load on there.
Well, what kind of stuff are we gonna do?
Nothing complicated. It'll be very easy, very little memory footprint.
Yeah, let's use the ends then.
Okay.
I mean,
yes.
you're welcome to, or do it locally, I guess, if you want to be able to do it locally later.
Yeah, so if you want to do this on, yeah, the only issue with that is that you won't have access to like the VS Code thing. But if you're on the yens, I imagine you have like Vim or Emacs or something that you know how to use. Or you can also use the VS Code SSH thing if you really want to. Here, let me add a little note on this. So if the install on the ends is very easy, you can just use module load Julia. Although I think there's a binary that's available to everyone in the namespace. I don't remember. Okay. My poll seems to have gone away. How do I get my poll back? Can you share show me the results for that? Okay. Oh, okay. Actually, this is the first time I'm happy about people being on Macs. Because your terminal is the same terminal as my terminal, more or less. So if you're on Windows, this will be a hoot, because then I have to show you what backslashes mean. Okay, that's perfect. All right. All right, so right now we're going to install Julia. You have a couple of options. If you want to do it on the yens, you're going to get into your typical procedure of getting onto the ends, and you can just call module load Julia. That's it, you're done. If you're going to do this on your computer, which I kind of advise a little bit because I want you to familiarize yourself with how the pathing works and kind of how to install it, you have two options. So the first one is just going to the website, julialang.org/downloads, and I will put this in the chat. All right. And then you download your binary. Ignore the current stable release 1.7. I'm going to skip to this and use the long-term support version, which is the one that's like, has a longer lifespan. So go and find the binary for your operating system. Okay, so you can do this if you want to. There is a slightly easier version. So if you're on Linux, or I'm not sure if this will work on Macs, I'm not sure. If you're on Linux, you can run Jill. And Jill, you can basically just run, let me see here. Yeah, you should be able to run, okay. If you're on Linux and you want to not suffer that much, just download Jill and you can run that bash script. There's a one-line command that'll basically download the binaries for you. It'll add them to your path. It'll do all that stuff. Or if you're a Linux user, I presume you already know how to add stuff to your path. You can figure it out. That's the fun part about having Linux users in the class. I can tell you to figure it out, and it's your problem. Okay, if you're on Windows, this is a very simple installer. And if you download the executable installer for Windows, you'll see a checkbox that says add to path. Make sure, I believe by default it is unchecked. You should check it. It'll make your life a little bit easier. But I'm going to hang out here for a couple of minutes. And if you start to run into problems or weird behavior, please let me know. So this is kind of like a sit and wait for people to install things kind of moment.
So does a lot tend to change between Julia versions these days?
No, not really. Julia has kind of fixed feature parity now. So, everything within the 1.0 major release is, basically fixed. Everything in there is kind of new, new features, more or less. There's nothing that breaks really. There's been a couple of times where like some compiler passes get really screwy, where like we kind of have like performance reversions or, performance hits. But those are usually fixed pretty quickly. 1.65 is just like recommended. The long-term support is recommended for like institutions or people who kind of sit and wait. And in general, the differences with like 1.6 and 1.7 are not that big. But yeah. Okay. And if you want to dump in the chat, you can just like type, hey, I did it. And so I can kind of start to get a sense of like who's managed to install this. And if you're like running into problems, please let me know. This is an interactive class. Done, done, done. Okay. Wow, you guys are great. Stanford really coming in. This is awesome. This is so much better than teaching master's students. No, I'm not. I'm going to take that back. I love my master's students. Go ahead, sorry.
Is there a wrapper you'd recommend? Sort of like RStudio for R. Is there one you'd recommend for Julia?
Yeah, we'll talk about that in a second.
Okay.
Yeah, I have a couple options, but in the short answer is VS Code, Visual Studio Code, and I'll show you how to install that as well. There we go. Joseph's got the REPL up to give you a sense of what Joseph is referring to. If you open up your terminal after you've installed it and you type Julia, you should get something that looks like this. And this is just kind of a lovely little window here. Always feels really nice to me to see the ASCII Julia thing. Okay, let me see how many people. Okay, so I'm by my count, I've got 12 people who were able to install out of 30. Okay, 13, 14, 15, 16. Okay, so we're about halfway through 17. Okay, cool. 18, 19. All right, solid. Is there anybody who's having any difficulty whatsoever or is currently in process? Okay. All right, I'm going to press forward. If you do start having trouble, put it in the chat, please, and so I can kind of go back to it as needed. Okay. All right. So, how to edit Julia files? All code is just text files. Well, most code that people write is text files. And Julia code is no difference. By convention, we use .jl as Julia extensions. So if you're writing a file that contains Julia code, typically you'll put .jl at the end of it. But as you may know, the last two letters of last 2 or 3 letters after the period don't actually mean anything. They're just conventions for the most part. So you have a lot of options for what is your text editor. VS Code, so is kind of the one that people suggest the most. So if you are the person who wants the kind of like flashy, kind of fast one with like good Julia support, you can go get it here. And this, I believe, if you're a person who's on Linux, you can install this on the Snap store. I think there's like a Flatpak version of it too that's pretty good. So there's also zipped up packages for it. So Visual Studio Code is the one that the Julia ecosystem recommends because it has like debugger support and all kinds of fun stuff like that. If you don't need that and you want to be just cool, you can use Vim. There's a good package for Vim support or for Julia support in Vim that you can install that with any of your package managers. I'm not going to walk you through how to do that. There's Emacs support. There's a good Emacs support thing. If you're an Emacs nerd, I suspect there's a couple of you. Or there's also good, Julia supports Jupyter kernels. So if you want to, use Jupyter Lab or Jupyter Notebook or whatever, those things are also there. And you may have to do a little bit of work to do that on the side, but I recommend VS Code for right now. If you're working on your local machine, or even if you're working on the Yens, you can SSH into it with VS Code. It has a really good remote work option. Okay. So I'm going to alternately switch between VS Code and this, which is a Jupyter Notebook. So I have both of them up, but I'll show you how I work in VS Code because it's important and useful. Okay. Questions on editing? I'm going to leave you to install an editor of your choice.
Question, is there a right extension for VS Code for Julia?
Yes, there is. So if you pick Julia, and the author is Julia Lang. So if I go to wow, the two Emacs nerds showed up here.
Is it bad that the GitHub says build and test failing? Is that an issue?
It is not an issue. That's kind of a known issue because it's running on nightly. So don't worry too much about that. For which thing? For the you're good. You're in the clear. So this is the one. So if you go to extensions, which is the little bricks here, you can do Control-Shift-X to take you there if you want to. You can type in Julia, and its author is Julia Lang. This is an incredibly good VS Code extension. So if you're on this, excellent. If you're on the Emacs side, that one's pretty good actually. I actually use it a lot still. I'm like trying to wean myself off of Emacs a little bit, but it's hard because I like Emacs. Okay. Alrighty. So does everybody have some kind of editor? I'm presuming. I'm just going to march forward and hope that you've got it. And if you don't, please let me know if you're having some kind of trouble or you get stuck. Alrighty. So I walked through how to do this. So the first two things are something you should do right now or have done already. And then I want to make a folder for just this course on your desktop somewhere on your machine so that we can keep all the code in line. So what I'm going to do is I'm going to go to this Julia bootcamp folder that I've made, which is on GitHub, by the way. I'll share the link after class if you haven't seen it already. And I'm going to create a folder in session 1, which is today's class, and I'm just going to call it live. And inside of the live folder is where I'm going to put all of my VS Code scripts, and I'll put these up on the GitHub repo so you'll be able to have them after class. But this is where I'm going to dump all of my code. Okay. If you want to do this, you can open a project if you want to. If you have it on a different thing, I've already opened this folder in VS Code, but you can go to File, Open Folder, and then navigate wherever you want, and that'll be your project thing, and it'll kind of keep all of your code easily visible. Okay. Alrighty. And if you're not on VS Code, then you're good.
Hi, is there a quick way to link the GitHub folder to the VS Code?
You probably want to clone it first, if you're familiar with how to do that. If you are not, then probably just keep a folder off to the side for now. But you should.
I think.
Yeah. Okie dokie. So I'm going to assume that you have VS Code or some editor, and you figured it out how to get it to work with Julia. You have a folder somewhere to keep files. I'm going to assume that you know how to get to this folder and that you remember where it is, because that seems to be a problem sometimes. And if you're in VS Code, that you've opened that folder in VS Code so that you can access it, add files to it, that kind of stuff. If you were not here, please let me know. Okay. Okay, sorry, there's a cleaning person coming in. Okay. Oh, all right. Well, I guess I'm wearing a mask now. In a room that only I am in. Okay. For days and days and days. Okay, so your first Julia program is we're going to do Hello World. So Hello World is like the common script that people have to let you know whether or not your code is working. So, and to show you how to like interface with things. Okay, so I want you to make a file called helloworld.jl and put it in this folder that we've made. The shortcut for this is in VS Code is Control-N, which opens a new buffer, but it doesn't save it yet. Okay, so I'm going to do this on my side here. So hopefully you can see VS Code over here, and let me make this nice and big. Okay. Okay, so I'm going to make a new buffer here, and I'm going to hit Control-S to save it. And I'm going to put it in my live folder here. And we call it hello world.jl and save it. Okay. Well, it doesn't like that. Oh, lol. Okay, that's why. Okay, so you should have an empty file that looks something like this. Okay, so this is all we're going to put inside of our script. It is going to be println, which stands for print line. And then on the inside of it, I'm just going to put a string that says hello world. Print line, hello world. Okay, so I've saved it. So this is about what it should look like. I'll put this in the chat so I can move on to the next slide. Okay, so now we're going to need to run it. This is like the next big step. Okay, so the interactive way is to move your cursor. You know, if you have the Julia VS Code extension, you can just put your cursor on top of the line you want to run and hit Control-Enter. And it'll spin up a little bit. It takes a second to precompile the VS Code server, which is a little bit messy. But at the very least, it'll kind of keep everything inside. And I will see hello world. The alternative, if you're working in kind of a terminal world, is I'm going to open this up. So I have my little terminal here. I'm going to navigate to my Julia bootcamp folder here. CD stands for change directory, which means move to a new spot. If you're not familiar with that. And then I'm going to go to my live folder, and I can see my hello world script is in there. I can either start up the Julia REPL and type include, and then the name of the file I want to run, which is hello world. It'll print out hello world for me. Alternatively, if I'm back in this thing, I can just have it execute hello world directly and then exit after running the script, hello world. I said hello world, but the world did not reply. That is not a bug. The world is just very disrespectful. Okay. All right. The second one didn't work for me. So if the second one didn't work for you, which I'm assuming by which you mean anything that's in the terminal here, make sure that it's actually, you're actually pointing to the folder, right? So
like include works fine. Just when I do Julia, the file name, it just doesn't print anything.
That is
Did you-
interesting to me.
That was the case for me too, but it was because I hadn't saved it.
Oh, there you go. Yeah, I see.
I was able to interactively run it in the REPL without having saved it, which felt
Do I need a symbolic link something? Is that what's being put in the chat?
I don't know that you'll need to do the symbol. Like if you can access the REPL, So if you type Julia and the REPL comes up, you shouldn't need to do the symbolic link.
Okay, yeah, because the REPL comes up just
Okay, then stick with just running include for now,
Okay.
and then we can
Sounds
chat
good.
later and figure it out, and I'll
Great.
see if I can replicate it. Okay, so this should basically be where everyone is. Okay, I see trash can guy has come and gone. All right. Okie dokie. All right, so if it went well, which in some cases it did not, you should see hello world. If anything broke or isn't working, which it sort of is, please let me know. Okay. So going forward, I don't care how you write your code. You don't have to show me, it's for you. You can put it in text files, you can run it in VS Code, you can type it directly into the REPL if you want. That's a perfectly valid way to do it. I don't care. So during concept checks, I'm going to make a separate file for each problem so that you can see how I write code in kind of like a normal environment. Or you can just dump, you can dump your own code in one big file. That's totally cool too. Okie dokie. Any questions on any of this before we move on from like how to set things up and get them working? Okay, cool. So let's start getting into the language. So this will be kind of like the fun part. So the natural place, I think, to start with any kind of language is what is the core kind of construct? And in this case, I think probably a variable is a good one you could pick. And so these variables as if you're an R person, the thing to the left of an equal sign or an arrow sign, which seems to be roughly equivalent for some reason, but people treat them differently in R. So a variable is a symbol, X, that we bind or assign a value to. So in this case, I'm just going to put the number 2, the integer 2, inside of X. I can print it out if I want to. So this should print out 4 if you run this, because it's going to look at X. It's going to say, oh, that's a variable. It'll say what's inside of X. It's 2. So this will be 2 plus 2, which equals 4. It'll print out 4. It's going to do some math. So if I do some math here in the assignment, it'll do 5 plus 8, which should give me, what is that, 13? And then put that in X, should print out 13. I even helped myself because I knew I wouldn't be able to do the math. Hold on, sorry, I need to actually fix this. Okay. Alrighty. So in this case, we can also put strings inside. Any kind of thing you can put into a variable. And Julia is extremely permissive about this kind of thing because you can also do a lot of meta programming. If you're familiar with that is, we'll talk about that in macros. Probably not in this class, but far later. Okie dokie. So that's how you do variable assignment. It's very basic. Thing on the left, equal sign, thing on the right. So as per usual, variables don't have to mean anything. They have to start with an underscore or a letter. So A through Z, capital or lowercase, it's totally fine. And then you can put more or less whatever you want inside on the, anywhere inside of the variable. Order of operations is strictly enforced as per normal, right? So you're probably familiar with this, is like, making sure that if you're doing a sum of things and you want to take a power of the sum, make sure you put the sum in parentheses so that it doesn't, if you do this, it'll take red 5 to the power of hats times the other thing, and then it'll just add x1, which is maybe not what you want. So please excuse my dear Aunt Sally is your friend here. Okay, and then print line is how you actually get it to show to the REPL. You can hide this if you want to. In my case, because I'm running this on a Jupyter notebook, it'll well, the Julia REPL will also do this. It'll actually it'll just try to display the last line in whatever code block you ran. So in this case, it's trying to print line answer. These are both equivalent. Okay. All right. So in Julia, by convention, we use snake case. So snake case means no capital letters for variable names. So if you have a very long variable name, you typically keep it, lowercase letters separated with underscores. This is the alternative that's called camel case, which is, first letter is uncapitalized lowercase, and then the beginning of second words start with capital letters. Don't do this. People get mad at you if you do this in Julia. But also if they get mad at you for this, then they should find a new hobby, I think. So you can also, variables have to start with a letter, underscores, and there's a couple of Unicode characters that you can use as well. So
just letting you know that we are at 10 o'clock.
Oh, shoot. Thank you. Excellent. I'll finish this up and we can go on a break. Okay. And if you want to define a constant variable, if you know what that is, I will talk about this, not today, but if you want to define constant variables that are in global scope or even local scope, you can declare them with const just before the name of the variable. Okay. So if you know what const is, that's important. All right. So we're going to take a break here. And then I'll be milling around in case you want to ask me questions. And we will be back at 10:10 Pacific time. Okay.
Cameron, just quickly, I'm getting an error when I try and change my directory in the actual
inside of Julia.
Yeah, inside the Julia. Do you just have I'm sure I've just got not enough slashes or something.
Okay, sorry, what's your okie dokie. All right, so welcome back everybody. It is 10:10, so I'm gonna continue with the lecture here. If you recall, just before the break, we were talking about variable conventions. So here's a concept check. I don't need the breakout rooms for this one. This is a purely in your head session. I want you to look at these and just kind of do some mental math. This should be fairly easy if you've worked in any other languages. But I want you to do Q1 and Q2 separately and see if you can guess what the output is going to be. And one of these is a trick question. So I'll give you like a minute or two to just kind of stare at this and see what you can come away with. And you can check after by typing it into the REPL or writing a little file for it. I love a good trick question.
And this is correct as written.
This is correct as written. Okay. Correct as written. Okay. I'll give you like 10 seconds on this one. Think fast. I don't know why I said 10 seconds. That's like a really bad way to get to thinking correctly. Okay. So for question 1, A is going to be equal to 3. So every time we see A, I'm just going to replace A with 3. A plus 1, that's 4. B equals 4. C is now equal to B, which is we just established as 4 times A, which is 3. So this should be 12. So print line should give us 12. Okay. Okay, now we have 3 variables in scope. Q2, x1 is going to be equal to 6. X2 is going to be equal to x1 divided by 2. That should be 3. So we have 6 and then 3. X4 is going to be equal to x3 plus x2. So what's x3? Well, we didn't define it. So there is no x3 here. So we'll never actually get to print line x4, and we'll never even finish this slide because we'll throw an error because we have an undefined variable, which is x3. So that's the trick question, right? This is like the eagle-eyed. Come on, let's do it. Okay. Any questions about that? That one's pretty simple. Just define your variables. If you're going to use them, they should exist first. Julia can't solve that problem for you. That is, unless you're in it, like Haskell can do this. I don't know. Even then, it's like I'm not sure. That's like a whole other nightmare. Okay, so I'm going to talk about the primitive types in Julia. So much like any other language, Julia comes with a whole set of primitive types. These are like the core constructs of the language that are just always available to you. Things like numbers, strings, characters, that sort of thing. So you have Booleans, which are true and false. If you come from the Python world, you will note that they are missing. They do not have the capital letter. They are lowercase. So true and false are reserved words inside of Julia. You can't use them for anything else. They mean true or false, 1 or 0. Integers. So these are typically denoted by int or uint if you work with unsigned integers. Unsigned just means I don't care about the negative numbers, so I have more positive numbers. If you're familiar with that, what that means. They come in int 8, int 16, 32, 64, and 128-bit. So your computer will default to whatever your processor's your processor architecture is meant for. So if you have a 32-bit operating system, Julia will use int 32 by default for you if you do not specify another one. If you are in a 64-bit system, which I think is most people at this point, unless you have an older Mac, I think those are like 32-bit. You'll end up on int64. So all of my integers are going to be int64 in the session because I'm on a 64-bit machine. Floating points, we have 16-bit, 32, and 64. So those are anything with decimals, that's a floating point number. And if for some reason you're working with extraordinarily large numbers, like maybe you're going to quit economics and go work in astronomy, you can use big int and big float. And these are arbitrary precision, arbitrary size values. So you can have 1 times 10 times to the power of 12 to the power of 2 type numbers, right? Your computer may run out of memory, but it can try. I do not recommend using these because they are incredibly slow. And if you are working with, very, very large numbers, you need to do a little thinking and see if you can make them smaller somehow. I recommend just subtracting a bunch of numbers. Subtract int, it'll make it work better. Okay, so these are kind of the core numeric constructs. The primitive types for some of the other things are strings and characters. So the type name for something is called string with a capital S, and they are surrounded by quotes. If you come from R or Python, quotes and apostrophes are the same. In Julia, they are not. A apostrophe indicates a single character. It indicates only one letter, basically. It's not just letters, but it's one character. So do not use these interchangeably. It will get mad at you if you try to put apostrophe around hello world. Typically would work a lot with strings, but you can get some performance if you switch to using characters. And the next thing is if you work with complex numbers, I don't know, maybe you do, maybe you have weird complex eigenvalues or something like that. They are supported at the language level. They're a core construct to Julia. And you can write them by putting the imaginary portion of your number when putting an IM right next to it. So if I do this, so if I do inum and I create a little variable here, so I can do inum plus 2, and you'll see that it takes, this is not a non-complex number, a non-complex integer, and I'm adding it to inum, and so it adds it to the real part of the number. So 3 plus 2, the imaginary number, and then I can add, all kinds of other stuff too. So when you're working with complex numbers, it just kind of goes through. There's no problem with working with complex numbers. You don't have to think very hard. They just happen, and it's totally okay. You can also do rational numbers. A lot of people are really amazed with rational numbers. So if you put 2 forward slashes, it keeps the ratio of the numbers. If you do 1 forward slash, it evaluates it into a floating point number. But this is a really good way to track ratios if you really, really want to, if it's important to you numerically, because sometimes you can have some very strange ratios that don't map directly to a floating point number, because floating point numbers are stupid, and you always end up in weird little gaps that can't actually be you can't actually get to by floating points, but that you can get to by rational numbers. So maybe this is a good way for you to track things. Okay. Hello, pop up. All right. So there's a quick function in Julia called type of that says, tell me what the type of the thing is in the parentheses. So if I type 5 here, that's an integer. And I already told you, because I'm on a 64-bit machine, it's going to default to a 64-bit unless I tell it otherwise. So I'm going to get int 64. That's the name of this type. If I put a decimal, it's going to say, okay, that's a floating point number. So I get float 64. True here, that's a word, that's a reserved keyword that means true, Boolean true. So it gives me bool is the name of that type. Type of howdy, that's a string. Type of single apostrophes, remember that's a character, char. Okay, so type of is a really useful command if you're like not sure what the hell it is that you're looking at. So if you're like if you're ever confused about like what the value of anything is, you can type of. And in Julia, where types mean a lot, this is kind of a good thing to have handy. So if you don't know what you have, you can just type of and print it out and see like, okay, it's like a vector any or something like that. Okay. Questions about this? Anyone has any? Okay, this should be fairly basic. Okay, so Julia has all the arithmetic operators. You're probably quite used to most of them. So if you just put a plus right next to a variable, it just means x, whatever x is. You can do a negative next to a variable to make it the negative version of that. You can add two things together, subtract them. Multiplication uses an asterisk like everything else. Division is the /. You can also do integer divide if you want to have, if you just want to get the integer part of a division. And I believe, and you can type, you'll note that this is a Unicode character here, right? This is like a weird character you may not have on your keyboard. And if that's the case, one of the fantastic things about Julia is that it supports Unicode input by default. So if I type .div, /div, and I hit the tab key for autocomplete, it'll put in the Unicode character. And it's amazing. I love it. So you can do any Unicode character, if you remember from like, most of the commands are LaTeX style. So if you remember LaTeX commands for various mathematical characters, you can type them in here as well. So if you want like psi, you can do /psi, or phi or phi, or if you want like C because you hate people, you can do that too. Yes, Apoorva posted this beautiful algorithms repo on GitHub, which has a lot of really beautiful algorithms that are written heavily in Unicode. And if you need to know how to type a Unicode character, if you go into help mode by pushing the question mark key at the very beginning of the line, it'll put you into help mode. And I have, like, let's say I was able to copy this Unicode character from somewhere on the website and I hit enter, it'll tell you how to type it. So it'd say type /circ tab. So anytime you need to know the command to get out a Unicode character that you can see on a screen, you can just do quote and then type like circ. How do I type that? Okay. So, and the question mark go into the help mode thing also helps you with basically everything. It'll load the doc strings and teach you how to use whatever you want to. So if you're confused about a function, you can get it right there. Question mark mode. Okay. Power here, if you come from Python land, Python has the world's stupidest exponent system. It's 2 asterisks right next to each other. Nobody else does that. Just use the caret. The caret is the correct way to annotate powers, in my opinion. Remainder is, the percent sign. Okay, so arithmetic operator is very simple. All right. So for this one, let's see. If I want to do this one. This one's super simple. I think I'm finding that the audience is like slightly more advanced than I'm used to, which is a welcome refresher. Okay, so yeah, let's just do this one without the breakout rooms because I think it'll be quick. I don't want to do the shuffle. So I wanted you guys to define a variable called z, and you can do this in your little scripts, and you can put whatever numeric type you want in there. And I want you to print out the remainder of z with various quotients, so 2, 4, and 8. And I want to see what want you to see what happens when you change the value of z and rerun the code. If you want to tinker around, if you want to do this like a little more interestingly, you can do some advanced stuff if you want to, if you know how to write anonymous functions. And then, so I'll give you this if you want to. If you want to work with map, if you know how to do this, you can write a little function that'll run this across quotients 2, 4, and 8, things like that. And I'm not going to tell you any further syntax than that if you want to tinker around with it. But I just want you to like play with some of the math operators and just like type some words in. So this should be like super easy, not challenging at all. Okay. And I'll pull this up on mine so that I'll work on this one alongside everybody. Yeah, so if you're trying to do the advanced version, I'm assuming that you will replace quotients with a thing. And I'll give you slightly more than this. So for example, if you replace quotient, if you do this, quotients equals 1 and 2, this says give me an array of 1 and 2 with those quotients. So if you replace quotients with 2, 4, and 8, then you should be able to get out what the remainders are with respect to z. Okay.
We have a question in the chat from Lulu.
Oh, why is I am not negative I am? Oh, that's a good question. I don't know.
Not important. Just a little.
I don't know.
Curious.
That's a good question. I'm going to defer that to someone smarter than me. How about that? But I'll look into that and I'll see if I can figure out what's going on there. Okay. All righty. So I'm going to start typing this out on my machine so you can see like what I'm going to do here. So I'm just going to find this variable z. I'm going to put whatever number I want in there. Let's do 90. I like 90. It feels right. And then I'm going to do this the kind of a lazy way. So I'm just going to define 3 variables like this. And then if you're in VS Code, you can get multi-line editing by holding Control-Shift and then hitting the arrow key in the direction you want to move, which blows people's minds. And I cannot believe people lived this way beforehand. You didn't have to install these weird packages that don't work. So I'm just going to do Z and get the remainder with respect to 2, 4, and 8. And then I'm just going to call print line on these R1, R3, and R2. Okay. And because I'm using the Julia REPL here, I can just hit highlight everything with Control A and hit Control Enter, and it'll run it out. Okay, so I get 0, 2, 2.
Wait, how did you do the vertical thing?
So put your cursor somewhere, hold Control and then Shift, and then hit the up arrow key, for example. You can also hit the down arrow key if you want to go down. So I can, in principle, go all the way up. And like I can go to the end of the line, delete all the lines, that kind of stuff. And then if you want to exit that mode, you can just double tap the escape key, and that'll collapse it back to 1.
What was the shortcut for that one more time?
Control Shift and then up arrow key, or Control Shift down arrow key.
Does that not work for, does that only work for Macs or something, or?
It
It doesn't work on my Mac.
Yeah, it's not
doesn't work on your Mac. Oh, here.
You can do it when you do Control Shift Alt and arrow.
Oh, Control Shift Alt and arrow. Oh, okay, gotcha. Yeah, that's a different command of mine. Thank you very much for helping me with that. I'm going to trust the 50% of Mac users in here to like help each other figure out your nonsense ecosystem.
No, I was Windows, but still mine was weird.
Oh, damn. Okay, so it's just me. All right. Okay, perfect. Okay, so this is how I would do this the lazy way. I'm going to talk more about this, how to do this kind of the interesting way. I'm going to show you how to do, you know, I provided this more advanced way to do this, which is this map function. And I'm going to define what's called an anonymous function, which I'll talk a lot more about later today. And then I'm going to put 2, 4, 8. And then I'm going to do for each print line rems. Okay. Alrighty, and then I'm going to run this whole thing, and I get the exact same output. So basically what's happening here is I'm saying take each quotient, 2, 4, and 8, put them into this function where they're going to take the role of x, and I'm going to put them in the quotient side. So I'm just going to take z, which is a fixed number. I'm going to take the remainder of z with respect to x, which is going to be 2, 4, and 8. And then I'm calling this for each function, which just says go through each value inside of rems and print it out. So rems here is an array of 0 to 2. Everyone ignore Lulu. Okay, that's it. I'll ignore Lulu. Nailed it. No more questions for you. Okay. Excellent. Any questions on like how I did this or how I think about this or anything like this? If you're used to for loops, you can also do for R and rems, print line rems. This is maybe the more common way to do this. All right, cool. Let us proceed. All right, so there's also the whole suite of Boolean operators. So if you were used to working with like true, false, any of that stuff, Julia supports all of those. So it has all, you know, so exclamation point before a Boolean value means not that thing. So not true means negation, this is equal to false. You can use 1 ampersand or 2 ampersands. My preference is that people use double ampersands because that is what's called conditional short circuiting, which basically means if I have 2 ands next to each other, and x turns out to be false, it's going to look at x first because that's on the left. If x is false, we don't need to check y. We're good because we're doing an and operation here. We just don't need to look at y. Whatever it is, I don't care because the first one is false. And because this is an and, both x and y have to be true. And if the first one is false, that's all false. Okay. You can do a single ampersand if you want both x and y to be evaluated. There's some cases where you want to do that, but it seems kind of strange to me to have them separated by Boolean like that. The double pipe symbol means or. So if x turns out to be true, you're already good. This is an or thing. I only need x or y to be true. And if x is true, then I'm good. I can just continue with the next code and return true. Okay. So this is the same as or in, you know, various other languages that you know. And then there's all the bitwise operators. If you're like old school, like bit shifting C style nerd person, you might be familiar with like bitwise operators. I'm not going to cover these. They're quite performant, but they're a little weird to teach sometimes and can be a little complicated. So I'm going to ignore them. But if you know what they are, they're here. One of the only common ones I see is tilde x, which is bitwise not, which can be a little bit faster than the bang not, exclamation point not. Okay, questions about Boolean stuff? Let me see one. Okay, cool. So those are there. Okay, so I want to play around with some conditional evaluation here. So I'm just going to give you the syntax for if blocks. I'm going to talk about those more in detail later. But here's the syntax. Basically, you say if, and then you give it something that evaluates to true or false. In this case, this is a comparison. I'm checking if some number is greater than or equal to 15, which we can look here in the compiler in our heads tells us this is 16. Is that greater than 15? Yes. This will evaluate to true, which means we will evaluate the code inside of the block. So I want you to make two variables, var A and var B. Put any numeric types in these variables. And then print out var, it's complicated, the string, if var A is greater than 1 or var B is not less than 2. And try tinkering around with this and just kind of composing things and testing some weird, just some weird conditional evaluation stuff, just so you can kind of experiment with it. Okay. I don't know if we want to try the breakout rooms. I'm feeling like this one is also very easy because I have a hard one that's like, I want people to be in breakout rooms, but this one is like super easy. I don't know. How do people feel? Do you want breakout rooms? Okay. How do we clear? I'm not sure what you mean. Like clear the workspace, like clear all the variables? They had a function that did that, but it is gone now. So the best way is just to like exit the workspace. So just hit Control D. So if you want to exit Julia, it takes the standard exit command, which is Control D, and it dumps us out. I don't think it's worth it that much to clear. You don't have to think about that too much. Like it's pretty good at handling all that stuff for you. So, but that's a good question. I don't. That's correct. You do not need parentheses around your Boolean conditions unless they are fairly complicated. So the the order of operations for Boolean operators is not as well defined in people's heads. So it's usually better to be a little safe than sorry and put in parentheses around your Boolean conditions. If you're evaluating a lot of them, you have a lot of ors and nots and things like that. But if you've got like a couple of simple inequalities, you're good. Just no parentheses needed.
Like chaining ors or chaining ands is fine.
Yes, that's perfectly fine. You can have a million of them right next to each other if you wanted. And if you do the double bangs, it's actually really nice because then you can say, well, check condition 1, is that true? Check condition 2, is that true? If not, it keeps going until it finds it true. Oh, and Herschel had a question about like how to remove variables. So if this happens to you, you want to like get rid of something, like you think it's taking up too much memory or whatever. So like, let's say A is 15. And you just want to get rid of A, you can do A equals nothing. And that means because it's assigned nothing, next time the garbage collector runs, it'll just sweep it off. But yeah, they removed what used to be called the workspace function, which I don't even think, yeah, it's not even defined anymore. But that used to be what the purpose of that.
Question in the chat.
Oh, yes. I'm getting an error. Syntax is not a unary operator. You need something to the right of it or to the left of it. It's trying to do. Okay, so Joseph, the exclamation point that you have directly to the left of the less than sign, you want to do instead, you want to do var b is less than 2. All right, so in this case, this is what you want to do because you want to negate this whole operation. Yeah, there we go. Is there a way to use map for this? Maybe, but it would be hard. I probably wouldn't. It's probably easier in this case just to use like if statements and ors and stuff.
Cameron, do you mind embiggening your terminal a little bit?
Yes, I can do that. Absolutely. How's that? I could go a little bigger, I think. Okay. Yeah. All right. Okay. So I think we're probably in like a goodish spot for me to check in and kind of go through how I would do this. So I'm going to say this as concept 2. Okay. So I'm going to create my two variables, var A and var B. Var A, and I'm going to put in like 10 var B is equal to, I don't know, -2, something like that. Okay, and then I'm just going to do my if statement here. So if var A is greater than 1, or not var B is less than 2. Okay, and then I'm just going to print a line. Print line. It's complicated. Okay, so that's kind of a very simple kind of procedure. So Joseph had his intuition here, I think, was actually a very good one. I think it's a good point to bring up, which is that I think he did something like this, which is where you're saying, I want to negate this operator, which doesn't quite work. But actually here, let me try something. I want to see if this works. I'm hoping. Space before var B. Okay, damn. I was hoping. All right, but this is the way it'll work. There's only one negation equality thing, which is negative equals. That's the one that actually has a defined negation property to it. But this is kind of a good way to do this. Okay, and one thing I wanted to point out about short circuiting is actually we can make this much simpler. So for example, watch this. So what I'm doing here is I'm saying, check this. If this is true, then, and I have an and here, it means, okay, I need to go and evaluate the thing to the right. Okay, and so when I run this, it'll print. It's complicated because, you know, let's break this a little bit. So let's set var A to -100, so we know it'll fail this one, and var B is not less than 2. Is that right? Oh, here. So it'll actually print false here, because what's happening is it finds that this is false, and it sees that there's a double ampersand to the right, so to the right. So it says, I don't need to keep going. Everything past here is not important. So this line actually returns false, which is the last thing to be evaluated in here. So you'll tend to see a lot of stuff like this, particularly if you're trying to like make a directory, which is like not isdir some folder, and make path some folder. So this is a very, very common thing you'll see when you're working with data, where you say, okay, well, does some folder exist first? If it doesn't exist, then I need to make it. If it does exist, then this evaluates to true, and then, you know, or it evaluates to false, and so I don't have to actually make the path. So this is a very common pattern that you'll see, where people will do these really short lines, which I think some people like, some people don't like. But I figured this is something to have. So I'll put this in there in case that helps you. That's a good line to have. I use that like literally all the time. Okay. Questions about any of the things I've done in here, maybe a little bit about short circuiting, or about kind of this like conditional evaluation stuff.
I have a quick question, and if you don't want to answer it, that's fine.
Okay.
How are rational numbers compared to floating points and other numbers?
Oh, that's basically, we can talk about this in multiple dispatch a little bit, but basically all the operators are actually just functions. So you can look and see stuff like this, and you basically say n1 is like int, and n2 is rational, something like this. And then you can define all of those methods within. I imagine they have like some kind of like clever numeric comparison specifically for rationals that I hope means that you don't have to evaluate them as floating points. But I don't think I know like the correct answer for that. But Yeah. Okay. That was a good question, actually. I like that. We can figure that out. All right. 10:43. All right. Got 15 minutes before our long break. So we'll see how far we get. This will be amazing. All right. So functions are awesome. So functions, if you come from R or like Stata or something, you're like maybe not used to writing a whole bunch of functions. You should get used to it because it's amazing. Like putting stuff inside of little function blocks is like not just good programming, but it also gives you free speed. And it's not even just in Julia. Like putting free functions inside of stuff tends to give you free speed in a lot of cases, many languages. So just try and like, if you're like thinking computationally, you kind of want to put things in little chunks that are defined by functions. So if you're not super familiar with them, with functions or writing them, we'll be talking about it. But a function is just a construct accepting some number of inputs. Could be 0, could be a lot, could be an undefined amount of inputs. That's actually perfectly valid inside of Julia. It's just copy pasted code that we overwrite the insides of with whatever we were given into the function. So if you find yourself copy pasting code 2 or more times, you should probably just write a function. That's like a pretty hard and fast rule. Like I don't want to read your code, and if it's just got like huge blocks of code pasted 70 times and you just changed one variable every time, don't do that to me, and don't do that to anyone you know, and don't do that to yourself. Just write a function. Treat yourself with some love, okay? Write a function. So the most common function definition is where you say function, that's a keyword, then the name of the function you want it to have. In this case, I have chosen the letter F. You can put any Unicode character, variable name rules apply. It has to start with a character, an underscore, or a letter, or some underscore, or some Unicode characters. And then you specify arguments here. So X and Y, that means this function accepts X and Y, which means when I give it values, it'll assign those values to X and Y and replace those values within the inside. And in this case, this function just adds them together. There is a shorter way to do this. If you have like one-line functions, you can basically just say the name of the function, the arguments you want it to have, and then equals sign, and then you give it, whatever you want it to do with those inputs, and it'll return what's over here. So these are two of the ways to define functions.
Cameron, is the first function actually returning something or not?
It is. By definition, it returns the last line in the function.
Oh, I see.
But you can make it explicit by adding return here if you so choose. These are equivalent. That's actually a good intuition to have, which is that in Julia, every single thing returns whatever was at the end of some series of imperative statements, without exception. If you didn't want this to return something, you could put nothing here or return nothing or something like that. Mm-hmm. There's not a whole lot of good cases why you'd want to do that, but sometimes it happens.
How about the semicolon operator? It seemed to me that if you put a semicolon, that it would suppress the output, the yes. Evaluation. Is that correct?
It doesn't suppress the return value. It's still returning something. It's just not printing it to the screen. It's like a please hide this from me, but it's still returning something. So functions are called. These are definitions, which means nothing's happened yet. They just exist. And then they are called. And when they are called for the first time, Julia says, oh crap, I have to do some stuff real fast. I have to like figure out how to use this function. So it'll take your inputs, it'll try to infer the type of the outputs, and it'll generate a bunch of machine code for that particular function. So it can optionally return something if you want to. We talked about this a little bit, but I want to try this with a polynomial function. So everyone should be kind of familiar with like really simple polynomials. This is a bivariate polynomial that's kind of like lazily defined. I've suppressed a couple of the values in here. But I'm just creating a function. I'm calling it poly. It accepts 2 inputs, an x and a y. And it returns 3 times x squared plus 2 times y squared minus the cross product. So this is 1 times the cross product. I can just delete that because it doesn't do anything. Okay, so it's just going to return this value. And I'll put this in the chat for people if they want to copy paste. Alrighty. So we've only defined the function. Nothing's happening yet. Nothing's going to happen until we ask it. Until we ask it to do stuff. Okay. So we're just going to call the function by providing it some inputs. You'll note here that this is technically an integer, and this is technically a floating point number. That's perfectly fine. Julia doesn't care about, you know, intermixing. There's no like real type promotion. It's just that multiple dispatch at the back end handles all of the cross promotion for you, such that when you do arithmetic operators on mixed types, you don't have to worry about it. Like this is not OCaml. You don't have to do like this nightmare town stuff that you normally do with like integers and floating points, which you don't have to worry about because if you work in R, because everything's numeric. So poly, it'll evaluate it. You'll note that it gives us a floating point number because it's got decimals. And now our line of code is compiled, so I can just call it a bunch of times. Okay.
Question in the chat.
Oops. Yes, here, let me pull it up. Why can we drop the asterisk at the beginning? I got rid of this because it was just 1 times. So that operation is like kind of meaningless. So, you know, if it was 2 times, then yeah, like that changes the output. So I can leave it in. That was just I don't know why I left 1 asterisk 1 times in there. That was like
Cameron, this was about whether you have to write 3 star X versus 3X.
Oh, yes. Okay. So Julia has like a little bit of syntactic sugar such that when you type, so that when you do this, actually here, let me. So if I do X equals 2, and then I type 2X, it'll infer that as 2 times X. So this doesn't always work. It's it's another kind of lazy thing to do. But if you have just like simple variable name on the right with no parentheses, and you have a number before it, a constant before it, then it'll infer that it's meant to be multiplication. Thank you for clarifying that, Josh. Okay. Okay. I'm wondering if I should skip this one for time because I want to get to the type system. Yeah, why don't we do this? All right. So this one will be a little bit harder, but I want people to have like some experience with like tinkering around with this. But basically, I'm going to give you a single univariate polynomial of degree 4, right? Or sorry, this should be degree 3, shouldn't it? And it's basically just defined this way in math. So it's theta 1, which is some coefficient, times x cubed, so on and so forth. So it accepts 4 thetas and 1 x. So this function should have 5 arguments to it. All right. So your the first thing I want you to do is write this polynomial function. So it should have 5 inputs, the x, and also each of the thetas, theta 1, theta 2, theta 3, and theta 4. And you can use whatever variable names you want. I don't care. One of the PhD students at University of Oregon, she uses spicy and extra spicy. So you can do that too if you wish. And then I want you to write a second function called h that accepts only x, but it evaluates g at 4, -3, 2, and 10, going from theta 1, theta 2, theta 3, theta 4. Okay. Let's see. Okay. I'll leave this in. Yeah, I'll keep us up here and we don't have to do the breakout rooms for this one either. I think I'm just going to retire the idea that I'm going to try breakout rooms. I'm so sorry, Riley. Riley was very helpful.
Okay. Cameron, have you told them about writing Greek letters?
Yeah, we went through it. I did the whole backslash.
Oh, sorry. Okay.
Thing. I think there was a brief mind blown expression I saw in the video. It was pretty great.
Cameron, how do you make the underscores for Greek letters?
Like subscripts. I believe. Yeah, that one's a little trickier.
It's backslash underscore.
Yeah, backslash under like
tab.
2. Yeah. So if you want to do that, you could do this.
Right.
Sorry, how did you do that?
So I did backslash theta and then tab to complete, and then backslash underscore, and then the number you want. So backslash underscore 2, and then hit tab, and it'll convert that to a subscript.
Thank you.
This is super cool.
Yeah, I mean, one thing I will caution about using superscripts and subscripts and like hats and stuff is they do not follow the same mono width formatting, so they can kind of squish your code up and make it look really weird. And it's also hard to write if you have somebody who does not know how to do backslash entry for LaTeX characters. So we did this a lot in Turing for a couple of years, and then we were like, no, it's just theta 2, right? So if I type this, then people understand it, and they can type it in chat, in like Slack, when they're trying to figure out how to use something. But if you give them this Unicode character, it's really easy to say, hey, I'm better than you. You can't type this character.
Cameron, do you mind revealing the slide one more time?
Oh, yes, of course, sorry. All right, how are we doing on progress, folks? I don't know where people are. I will take a rough description of whatever it is you have. All right, Joseph's done. Ooh, look how fancy, quick Joseph is. Done, question mark. Okay, well, that's concerning. Okay, done. Okay, so we got a couple people rattling in. I'll give you a little bit longer, and then we'll see if we can get some more folks.
Can you give us a sample evaluation of H so that we can know if the numbers are correct?
You should be able to call. So you should be able to evaluate. Now, let me pull this up. So you should be able to do G. G1 for -3 to 10. And that should be exactly equivalent to H1. So pick an X, and then they should give you the same output. Can the theta sign be used as a variable when declaring the function? Do you mean like an argument name? If so, then yes. Yeah. So you can do something like this. So if you do function G, X, theta, theta 1, theta 2, so on and so forth. Like, that's perfectly acceptable. Okay. All right. I'm going to start going through my answer here, so you can see kind of how I would do this, and then after that, we'll take a break. We'll take our long 15-minute break. Oops. Oops, concept 3. I had to switch to the quieter keyboard, so you guys didn't have to hear me clicking and clacking, and it's making my fingers really, really clumsy. Okay, so I'm going to create my function G, and I'm going to do. I'm just going to call these T1, T2, T3, T4, just to make it nice and easy. And then I'm going to do my return value, which is going to be T1 times X cubed plus T2 times X squared plus T3 times X plus T4. Right, so that's just our intercept term. And then I'm going to use the shorthand evaluation because what I'm doing here is this is like in terms of like computer science terms, this is like I think called a partial evaluation is what you're doing, or currying, I guess is like maybe the better way of describing this. But I'm going to define h of x as equal to g of x, and I'm going to give it 4, -3, 2, and 10. That should be -3. Like this. So what I've done here is I've defined a new function called h, and note there's a single equal sign here, which says, you know, assign to h of x this function. So when I call h of 1, it should give me 13. So everyone should have something like 13, or exactly 13. I hope it's exactly 13. And you can, you know, try this out with all kinds of other things too. All right, so you should be able to get all kinds of fun numbers out of this. Okay, so this is kind of one way to do this. Well, when we get into like vectors and array types, you should be able to kind of take around with this and get some more interesting stuff. Okay, questions on this before we go for our break? Okay. Then I think we're going to take a break from 11 till 11:15. Yeah, so I'll be hanging around and like doing some like little
works with
Thank you. Excellent timing on the recording. Okay. Okay, so I'm going to be like kind of like jumping around a little bit to make sure that we can like get to the important things I want to get to for the project. I'm going to leave this off to the side for now because we'll talk about it a little bit. We talked about return. And so return is a special short key a little bit that tells you to exit a function immediately, wherever you are. So I wanted to give you a brief example of this so you can kind of internalize how that works, because some people aren't used to working with return statements. So I've written this function called aces, which just accepts one argument x. It checks if x is greater than 5. If so, it calls this return statement. But note that I've had this other line below the return statement. I will never get to this line because return immediately precedes it. And when that's the case, we always dump out of a function and we return x plus 5. Okay, so if x is not less than 5, then we return this, and it doesn't really matter that we're exiting early because it's the very last line in the function. So I wanted to give people to keep that in mind. You know, when you're writing return statements, make sure that you're done when you're returning something with a function. Okay. Default return values, we talked about this last line. That's the one that gets returned. So I'll skip over this one. Oh, this one's important. So you can return as many things as you want. You just separate them with commas, and that creates what's called a tuple. So for example, I've created a function that accepts A and B, just two inputs, A and B. The first thing it's going to return is A times B. The second thing is A divided by B. The second one is the sum, and the last one is the difference. Notice that they're separated by commas. This is actually what's called a tuple. If you're used to this in Python, you may be used to explicitly putting a parentheses around them like this. But in Julia, you don't necessarily have to do that if you don't want to. And so it'll create a tuple with 4 elements inside of it. If you don't know what a tuple is, that's okay. I'll show you in just a second. So when I call this function with A equals 1 and B equals 2, it'll give me 2, 0.5, 3, and -1. Okay, so you can do this if you have like a lot of things that you're doing inside of a function, right? So you know, like one of the things I'm hoping to get to today is like working through bootstrapping and like having some OLS function that gives you like your estimates and the bootstrap standard errors together. And those are 2 different things. And it takes a lot of work to get to those 2 things sometimes. And so you want to return both of them if a function has them available to it, so you don't have to repeat computation. Of course, there's more architectural things you can do to make that easier. But sometimes it's just a good idea to return things, multiple things in a tuple. And tuples are really, really fast in Julia, so you're not going to get like too much allocation overhead. And these are not going to be like a huge nightmare to return. One thing you should not do is do brackets instead, which denotes an array, because then you run into all kinds of stupid type constraints. So just don't do that. Do parentheses if you're returning multiple values. I'll talk about that more in a second. So this is an example of tuples. If you're familiar with them from other languages, you'll remember that they are immutable. And in Julia, they are immutable as well. You cannot change anything inside of a tuple. It's ordered, so you can't change the order. And the thing in spot 1 is always the thing in spot 1. And they're fixed length, so you can't make them bigger without creating a new one. Okay, so these are super, super popular and very, very useful. You can access any individual value inside of a tuple with brackets. So here I've created a tuple called with 5, 10, and 15 in it. I'm assigning it to a variable called a tuple. And if I want the first thing out, brackets 1, and then I get 5 out of this because that's the first thing. And we use one-based indexing in Julia. I don't care about your opinions about one-based indexing. That's what's happening. So we can do what's called unpacking. This is another thing that you might know if you've written a lot of Python, which means if you have a tuple, you can unpack them into a thing that's left on the left by assigning them or in an ordered way. So here, I actually have 3 variables on the left. They're separated by commas. And on the right, I have a tuple with 15, red, and 8. If I print out C, you'll note that it is just 8 because we've matched up A with 15, B with red, and C with 8. So this is a really, really nice tool if you're working with things where you know that you're returning multiple values out of a function or out of an expression or whatever. So I just want to put that in people's minds that when you see variables on the left separated by commas, it means you're trying to do some kind of unpacking of the thing on the right. And you can unpack anything. You can unpack, I believe you can also do A comma B dot dot equals 1, 2, 3, 4, 5. Let's see if that actually works. Yeah, so in this case, B is the last 2 3s. It takes the first element, assigns it to A, and then it takes everything else and puts it in B. So if you're used to working in like Haskell with like lazy arrays, which I imagine nobody is because you shouldn't be used to working with Haskell, this is a nice property that you can do. Okay, questions about that? About tuples? And
wait,
you can
Cameron, maybe,
yes.
Maybe this is a good moment since you use that example with the lazy concatenation to talk about the difference between the data type that comes out of the concatenation and the tuple.
How do you mean?
So when you set B dot 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 is equal to stuff, the thing that came out wasn't a tuple, right?
Oh, that's because I used it as a so let's do B dot dot dot. I used an array there because I was being lazy. Red and 7. So when I print line B, it'll maintain the type of the tuple. So this is actually a new tuple that we've created. But this is a good way to like chunk it up. Like if you're like, I only need the first value of some iterable thing. So tuples, arrays, any kind of iterator, ranges, all that kind of stuff.
Okay, and that helps, thanks. And also, is there any overhead to creating new tuples is hard? Like, how should we think about the performance of, should we think about the performance issues of creating new tuples? Should we think about the performance issues of creating tuples with different types?
Creating tuples is cheap. It's incredibly cheap. So like the alternative might be like creating an array or vector. Vectors are awful if you're just like creating a bunch of them because you have to do all these allocations. You're not sure what the size is. They're mutable. You incur all these costs. If you have like a couple of things that you know you don't need to change, put them in a tuple. Like they're awesome. They're super cheap. And you can put whatever types you want. So for example, this tuple here is actually mixed type. It's integer, string, integer. And if I look at the type of this, type of B, for example, you'll see that it actually handles the types. There's one type for each spot inside of B. the first value inside of B is red, which is a string, and the second value is int64, which is 8. So the typing is really, really strict here inside of a tuple, so you don't have to worry about mixing and matching types, and they're fast to make.
Thank you.
Yeah, that's excellent question. I'm very pro tuple. I love tuples so much. They're amazing, like zero memory overhead, super fast to make. You can also make named tuples. If you want to know, if you want to be able to access the location, access something in a location of a tuple by name, you can just put a name right before it and then equals. You might know this from like doing named vectors in R. If you have like named vectors in R, these are way better. These are so much better than anything you could cook up in R. So for example, I'm creating a name tuple with thing1, thing2, and thing3 as keys. And if I wanted to get thing2 out, I just do dot thing2. I believe you can also do brackets. Let me see if that works. Yeah, that works too. So you can also do the symbol form of the name. Okay, so I tend to work a lot with name tuples because they have all the benefits of tuples in terms of allocations, memory allocations, but they also have the benefit, like the accessibility of dictionaries, right? Without having to incur the O1 like hash lookup.
Can you access an index by variable?
Access an index by variable. What do you mean? Oh, yeah, like, so if you wanted to do thing2, so for example, I could do ID equals thing2, and then I could do that. And here you'll note I'm putting a colon right in front of the name. This is what's called a symbol. And a symbol is a special, it's kind of like a string. It's meant for if you want to work with metaprogramming, but people use it as like a string alternative that tends to be less ridiculous than strings, because you don't have to track all the characters. It just maps to an ID.
Cameron, the named tuple is still immutable, right?
Yes, the named tuple is still immutable, which is also one of its superpowers, because most of the time you don't need to mutate stuff.
Yeah. So you can use it to access, but not to reassign. Yes,
and the unpacking works as well too. So you can do unpack it just the same way as you would with tuples. I'm going to skip that one.
Cameron,
you can do
so these tuples are immutable, but you can merge them, right? So
yes, you can merge.
Put in additional elements to the named tuple here, right? Is that correct?
Yes. So here I'm creating two named tuples, and what he is talking about here is doing merge name tup and tup2, right? And so this will create a new name tuple with Cameron, comma awesome. This is not technically mutability. What you're doing here is allocating a new tuple and creating it with the combined keys from all of the tuples. So you're more creating a new one than you are, and this can be really expensive. So like you don't necessarily want to do like a lot of merge calls. Like if it's like two tuples, okay, cool. But if you're doing this like hundreds of times a second, probably not a good idea. It's maybe better to work with vectors if that's where you're at. Did that answer?
So if I were to, for instance, create like a data frame in a for loop or something, I have seen some examples where people would create a named tuple to sort of store all the intermediate files and then assign essentially an additional row or column to the data frame that I'm trying to create. Is that something that you would recommend, or would you rather prefer to use a different, like an array or a list?
Depends.
In Python, I've been using lists for these type of operations.
Yeah, it depends. I think if you're tacking stuff on to something, like if you're just like adding, you don't know how many you're going to make beforehand, it's usually better to use some kind of array type. Because like tuples, they're meant for like, I have like 4 things and then 2 things, and maybe I want to merge them together, but probably not. Like arrays are, I need to expand these. I'm going to put stuff inside of this vector, and I need to change it a lot. Like that's kind of what it's for. So if you're expanding a data frame like regularly, you should probably not. because it has to do this reallocation nightmare every time. Even though data frames are pretty resilient to that in Julia, because they're basically just a bunch of vectors. So I guess I don't have a good answer for you. I think probably you're okay. If you're adding rows, it's probably okay. If you're adding columns, actually, I don't know. I'm going to defer that because I don't have a good answer for you. We'll see. I'll come up with that. Okay, but good questions. I wanted to go through keyword arguments. So if you have an optional argument, you can put it on the right-hand side of a semicolon, and you can add any other ones that you want. And by default, in this case, coef is just going to be equal to 2, right? And I can choose to override it if I want to, but otherwise, if I don't, it'll just work with what it's given. So when I call f2, it'll be 2 times 2 because coef defaults to 2. Okay. But if I wanted to change coef to 10, I can just do this. You don't necessarily need the semicolon in there. You can do a comma and it'll try to infer, but it's generally considered better practice if you're calling a function and using its keyword arguments to put the keyword arguments at the end of the function call after a semicolon. Again, you don't need to do it, but it's considered good practice. Okay, so those are useful if you need to change kind of default parameters of your function. But you can get yourself into some problems if your keyword arguments change the type of your function. I'll talk about that in performance, but just kind of be careful with using keyword arguments if you're like in performance land. Okay, any other questions about this stuff? Or I know we're kind of like sprinting through like functions and keywords and stuff, but this is a good place to stop and reconnect. We need to. Okay. So I'm going to get into the vector stuff, right? Because we all work with like numbers, a lot of numbers. I don't know a lot of people who work with one number. I would like that job. That sounds really nice. Like I can add stuff to this and divide this. I would love to. But typically we have a lot of vectors of data of people's, like panel data or whatever. And these are often well represented by vectors. So Julia supports natively vectors, matrices, which in Julia are restricted to be square, but you can also have not square, but two-dimensional, and arrays, which can be any dimensional. You can have like 19-dimensional arrays if you want, but they're kind of a pain to work with, as they are in every language. So, for example, everything that's surrounded by a bracket, that's a vector. Or, it indicates an array. It doesn't have to be a vector necessarily. It can also be a matrix, just like it is here. In this case, this is a two-dimensional array with, okay, here, let me slow down. This one is a vector. It has elements separated by commas and surrounded by brackets. So this is basically a list in Python or a vector in R. You can make rectangular arrays by separating elements within a row by spaces and separating rows by semicolons. So this is 2 rows. The top row is 1, 2, 3. The bottom row is 4, 5, 6. And these are all integers. Julia will infer the type of these vectors as int64, at least on my machine. Okay, so these are super handy to have. Julia has a pretty good way of expanding arrays if you need to make them bigger. So and the way we do that is with push, exclamation point, the name of your vector and what you want to push onto it. So the exclamation point inside of a function name means nothing. There is no, like the compiler doesn't see it. It doesn't care. It doesn't change the code. It's a social convention that Julia programmers have adopted to indicate that you are modifying the first thing. We're passing by reference something to push, and it's going to be different when this function is called. So for example, I'm creating a vector xs with 4, 5, 6, and 7 in it. I'm going to push 10 to the end of it, and then I'm going to print it out. So now xs has a 10 at the end of it. That's very common. Push is actually quite cheap relative to other languages. It's still not a great idea. the better alternative is to say, I know exactly how big my array is going to be and pre-allocate it. And the way you would do that is XS equals zeros. And then you specify a type. In this case, I'm only going to put in integers. It'll default to float for 64 if you don't give it a type. And I'm going to put in a 4 in it. Right. So if I do
in the chat for you.
Oh, thank you. Thank you. Can we push to a specific location? Yes, there's a command for it, but I don't remember it because I don't use it. You can push whatever you want to. I actually don't know what the behavior is if you push to a matrix. Just because that feels really weird to me. Yep, doesn't like it. Well, we can also try vector type. I don't know. Yep, doesn't like it. So no, don't push to a matrix. And I don't remember how to push to a specific location. It might be just push. Let me go check the docs here. Yeah, I don't remember. Sorry about that. I will send you an email, I promise. Okay, so I wanted to give you guys some convenience functions about how to, just to work with arrays because, they vary by language, but they can be very helpful. So length tells you how long the vector is. Or if you have a matrix, it'll basically tell you how many elements are in it. So if you have a 2 by 2 array, it'll give you 4 as length. Size gives you the size of the thing in a tuple. So for example, let me take this here. I'll do XS is equal to 1, 2, 3. And then I'll do a length XS, that'll give me 3. If I do size XS, it'll give me a tuple, a singleton tuple, with the first element equal to the how many rows there are basically in this column vector. So if I create a matrix where I do 1, 2, 3, 4, 5, 6, right? This is a 2 by 2 or 2 by 3, sorry. And I do size mat, it'll give me 2 and then 3. 2 is rows, 3 is columns, and this it'll give you a bigger tuple if you have like multi-dimensional arrays. And you can get out a specific dimension with (1) instead. So if you give it a dimension, it'll give you the 2. If you give it if you put a 2 that says give me the number of columns in this matrix. All right, so that works for data frames and everything as well. Okay. So length and size are very useful for you if you receive an object and you need to know how big it is. Zeros gives you a vector of zeros of length n. Okay, so in this case, I can do zeros 10. That gives me an array with 10 zeros in it. This is useful if you know you're going to create 10 numbers, because if I have like z's like this, and I'm like, oh, I solved for zs5, I know that this is 1.1. Then I can go back and change the values in here, and I don't have to deal with push. Because push is still quite costly because you have to reallocate the vector or do a little bit of like kind of shifting. But if you pre-allocate everything ahead of time, you don't have to worry about the memory when you do the compute and stick it into a vector that already exists. You can also create like multi-dimensional zeros by separating the elements with a comma. So in this case, this is a 5 by 5. If I wanted a 3-dimensional array, I can do 5 by 5 by 3. This gives me different pages, 3 pages here. I believe you can also add, I could make this a 4-dimensional array if I wanted to. You can keep going. If you're working with a 4-dimensional array, please do not call me. I don't want to help you. It sounds awful. But anyway, that's a very, very useful skill to have, or very useful command to have. Ones is exactly the same, just gives you ones. By default, it types everything as a float, but you can overwrite this with, give it an int, for example. And it'll give you, int 64 will be the type and it won't be floating points. So keep that in mind. If you're only working with integers, it might be nice to just like constrain it to integers from the bat, from the get-go. I think it works with Booleans too. Yeah, so it works with Booleans. So that's a really cheap matrix to make. Okay. Also generating random numbers, very, very useful. Rand 15 gives me a vector of 15 random numbers, and it follows the exact same syntax if you want to change the size. So 2 columns of 15 rows. These are random uniform variables, or pseudo-random. The random number generator is Marcin Twister, if you care about that. But you can change it. There's a, you can use like system noise or whatever you want to. And then the other one is rand n, which I imagine a lot of people here will get a lot of use out of, which is random standard normal variables. So if I want 15 standard normal draws, kaboom, you have just gotten a bunch of free random normals. Okay. Questions about any of the convenience functions? There's a bunch of other ones, like sum, for example, sum rand n 15. That just adds everything up. You can change the dimensions. So for example, if I wanted to do 10, I can do dims along, dims along axis 1, which means squish everything down in the rows, add up all the columns. I can change dims to 2, which means add everything up along the rows. So you can play with dims that, there are as many dims available as you have dimensions in your array. And this works for every other function, right? If you do using statistics, help if I could spell statistics. You can also do the same thing with like mean. Okay. So yeah, all the types are available to you, all the functions. Question?
Can you talk a little bit about the namespace type stuff? So like when you import something, everything is globally visible?
Yeah, so only the things that people have chosen to export. So a lot of packages use a lot of things internally, but if they don't explicitly declare exports, you have to access them directly by the namespace. So I would have to do namespace.statistics.mean if they chose not to export this. There's a difference between using statistics, which says, get me everything that they've exported. And then there's import statistics, which says, I'm not going to take anything that they export. I have to explicitly declare the module beforehand if you do import first. So this is a really good way if you want to avoid like namespace collision, is using import instead of using. If some people have been very careless with their exports, which sometimes happens. Okay. Go for it.
Way to view the variables and functions that are in the memory, like what we do in MATLAB or RStudio. I think this is a feature of the VS2. Possibly turn it on.
I know there is a command. There's something I don't remember. I'm going to have to defer that one, but it does exist. It'll tell you everything that's in your current module, your current namespace, which is main. Sorry, I don't have the answer for that one. But if you're using VS Code, I think it may populate. I'm not sure. Anyway, all the syntax for accessing things is the same as in MATLAB. If you've ever used any MATLAB, just replace the parentheses with a bracket. That's how you get values out and you set values inside an array. Okay. You can do ranges. So for example, if I wanted to get element 5 through the end of the array, I can just do 5:end. And end here is a special word in Julia, which means length of xs. Let me correct that. That's really handy. So you don't have to type like, in R, you might be used to doing like 4:length, whatever the thing is, which is really, really annoying. So in Julia, you can just do end. You can also even modify it if you wanted to. So if you wanted to go end -1 and get everything but the last value, you can do that as well. And it'll evaluate that, the relevant length. Just a colon by itself means get me everything in that row or everything in that column, basically everything in that axis. You can also kind of, yeah, I'll leave it there. So this is how you get ranges of values. All right, any questions about like slicing, things like that? You can use this to set values as well as get them. So xs equals randn 15. And if I want to set xs 1 through 5, I'm going to set it equal to 0. You'll note I'm doing this dot sign here, which is broadcasting, which means basically replicate the 0 and fit it into every value of 1 through 5 of xs. Now, if I go back and look at xs, the first 5 elements are zeros. Okay. All righty. So it works as well for this. So if you have if you just want to set a small chunk, or if you want to set a submatrix, like maybe you're working with block matrices, you can actually specify the block and then give it a matrix, and it will assign everything in the matrix that the smaller matrix into the block matrix of your bigger one. So for example, if I create 5, I can set the first value to 3. I can set 2 and 3 indexes 2 and 3 to 4 and 4.5. And then I can set 4 and 5 to 1 and 2. And when I look at it, I get this. So ranges are super helpful for that. Questions about this part here? Okay. Man, I don't know if we're going to get to the project. It's going to be a bummer. But I really want to. Okay. So map, I gave an example of this, but I want to kind of spend a little bit of time on it because I think it's important, which is map. You may be used to doing some kind of vectorization stuff for lapply or rapply or sapply or whatever the hell it is that R has. There's way too many of these apply functions. But in Julia, we just have map, and map says take a function that accepts one argument and map across a list or a vector or an iterable of things. So things to input here is a variable that can be anything. So it can be an iterator. So if I do what's 1 through 5, that's what is called a range operator that represents the integers 1, 2, 3, 4, and 5. It's not a vector. It can be if you want it to be, but it's not actually a vector. And it will return F1, F2, F3, F4, F5 is what that should be. It can also be an explicit vector if you have it. It can also be ordered sets or dictionaries or whatever, right? You can, basically anything that applies iterators, which is a ton of things in Julia, chances are good you can map across it. So here, if I create a doubler function, which just doubles whatever the input is, and then I call map on it, I will get 10, 20, and 22. Because I have 5 times 2, 10 times 2, 11 times 2. And you can also do the same thing with the range objects, as I mentioned.
Does this natively try to do anything in parallel?
No, it does not, but you can. So there's a package called threadsx, which isn't installed natively. And you can do threadsx.map. And then you can do doubler XS. And so if you have more than one, if you started Julia with more than one thread, it'll just dispatch this across all the threads or do all the ordering and everything for you. So threadsx is actually really nice for that. And if you don't use it, then you have to do locks and stuff for thread safety. This is what is called an anonymous function, which is a shorthand.
Ask you a short question. What is the advantage of using the map instead of just writing a vectorize function?
It is vectorization. It's cheap, free vectorization.
Oh,
it's about the same. Oh, actually, this is a good point. What is your language of choice?
Mine?
Yeah.
Oh, I used pretty much everything. I started with MATLAB.
Okay, so other languages are very good at burning people on vectorization. Everyone is like if you work in R or something, you're like, oh crap, loops in R are slow. And they're terrible. But Julia doesn't care. They're very, very fast. And so anytime, if you think that you have to work really hard to make a vectorized function, you don't have to. And there's actually a cheap free button that you can use to write a univariate one, which here, I'll actually do this right here. if I do doubler dot XS, putting the dot in between the function name and the argument tuple says, basically implicitly call map for me. This is a free way to vectorize a function. And so it'll go through each element of XS and it'll create an array using the doubler input.
So if you would time the performance, they would basically be equivalent.
Yeah, they should be equivalent or very, very much the same. There might be a little bit of function, like additional overhead in the broadcasting component, but I'm not sure of the implementation details. For the most part, these things are written really, really well in Julia. They spent a ton of time on them. So like I kind of trust their performance. I don't have to do my own benchmarking that much. But yes, very, very fast. Okay. You can also do what's called, like if you don't want to name a function or you have a function that accepts multiple arguments, you can do what's called an anonymous function, which basically says, this is also called a lambda in Python and several other languages, you may know it as. And so basically you just take the name of the thing that you want to use as an input, you put an arrow, and then you specify the function that the value that you want to get out as a function of the input. And so map is really good for this kind of thing. And it tends to actually be quite fast. This anonymous function thing actually works really well. So you'll see this a lot in code, but it's, in general, I prefer to actually explicitly define the function. So it's a little more readable. Here's an example of where that's useful. So for example, there's a lot of functions that have like 2 inputs in Julia. So for example, this takes x and y, squares x, divides it by y. But I have a list, and map is expecting something that will take one thing. And so I can give it, 1, 2, 3, 4, and then just specify fix y to be 3, basically. So you'll see this kind of thing all the time. Okay.
Can you walk through this one in a tiny bit more?
Yeah, sure. Yes, of course. So basically what we're doing here is we have a 2 input function here, which basically says 2 input function. And I'll give this like 1 and 2, right? So let's say we knew that y was 4. And we wanted to see how x changes as we fix y. One way to do that is to just map here by saying, I'm going to declare an anonymous function. And we can also make an explicit function here, which is just equal to 2 input function m3, right? Which is what the equivalent is here. And then replace this with map target 1, 2, 3, 4, like that. So these are now roughly equivalent, or they're exactly equivalent. And so now we're able to say, all right, we'll fix y and see what happens. If you have a set of configurations for this, there is a slightly better way to do this, which if you want to map across, you don't want to just like fix y to be 3. You could have something that's like called inputs here. You could do 1 and 2, 2 and 4, 3 and 4, and 5 and 6. And notice here I'm declaring these as tuples, right? So these are pairs of numbers. And let me see here what I could do. I'll do the same thing here. So I'm going to accept 1 input, which in this case is going to be a tuple, because each value in this list, there's 3 elements in this vector. Tuple 1, tuple 2, and tuple 3. And I'm going to call 2 input function with m1, m2. I'll do this with inputs like that. So if you like want to vary y as well, this is another way to do this. But if you know that y is always fixed, then you can just do this too, and you can kind of avoid having to deal with it. Okay. Alrighty. I mentioned broadcasting. Broadcasting basically just calls map for you. So if I want to do sign of everything, I just get a vector out. super cheap, super simple. Define a univariate function and you have the vectorized form of that function for free if you put a dot in front of it. Nice. Okay, I'm going to skip this concept check. I apologize. Okay, so conditional evaluation, if you're used to working with if blocks, this is how you write them in Julia. So if this evaluates to true, it runs this block and only this block, and it'll skip to the end of it. If thing ends up being false, it'll go to else if. Notice that that is one word, else if. And if another thing is true, then it'll run this. If not, it'll go next. And if none of the above is true, it'll run what's in else. You can also leave else out if you want to. You have to have if and you have to have end. You can optionally include anything else. So yeah, this is just a very common practice here. Loops. So loops in Julia are super fast, as I mentioned. So for loops are the most common one. And the syntax for this is for variable that I want to use in something that is iterable. So something that is iterable is commonly a vector. It can be an iterator or range. So another one here an alternative you could do in this exact case is 1:5, which means give me all the integers from 1, 2, 3, 4, and 5. And so you can print these out. You can basically put anything you want in here. And if you don't know what it's about to spit out, just print whatever is being assigned to I, and then you can kind of try to understand it in your head. But you can iterate across basically everything, as long as it's not a primitive type. Don't try to do that. You look like an idiot. Okay, so you can also iterate across across strings. So this will give you the character H, the character O, the character W, so on and so forth. If you have a dictionaries, which I haven't really talked about too much, but they're very useful, you can iterate across the pairs A and 1, B and 2. And you'll get both every loop, and they'll be in a tuple. Well, they'll technically mean a pair, but they're equivalent or similar.
Quick question in the chat here for you.
No, thank you. Okay, so Joseph has this line here. Let me put this up on. Sorry if I'm using you as an example, but you have really good questions. You'll note here what this actually is. So if you look at the for loop here, on the right-hand side, the iterable thing is actually a vector of ranges. So this is actually a vector of length 1, which has just one thing in it. So if I go back here and I get rid of just the brackets, it is no longer a vector. It is now actually just a range, which is a different iterable object. So now it'll print 1, 2, 3, 4, 5. There you go.
So the range itself is another data type.
It's another data type, and you can do whatever you want here. Like you can do like nested vectors, all kinds of crazy stuff. Yeah, I mean, you can even look at the type of this. So if you look at type of 1 through 5, gives me a unit range in 64.
Can you give a little bit of insight to why that doesn't just evaluate and why it's better for Julia, or why Julia has chosen to keep that as a separate type?
So for this one we keep this as a separate type because sometimes you don't actually want to get to all. You don't want to do the vector allocation to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? It's sometimes much easier to just like, you can do all this stack evaluation if you know what the last value was in your range. So if you know that the last value is 4 and you know that you increment by 0.1, you just add 0.1 to 4. And so then you don't have to do like pre-allocate this huge vector. And so you get way cheaper loops when you do that kind of stuff. If you want it to be a vector, you can just do collect. So if I do collect like that, it'll give me the vector of all the values. And just as a side note, you can specify a step size in here. So this will do increments of 0.1. I can collect that. Okay. All right, so we're coming up on new, oh, sorry, go ahead.
Just a quick question about the range.
Does it support like MATLAB ranges with customizable increments, basically? Like if you want to do step 2, or like you're going in decreasing order?
Yeah. So that's what I have here. So if you put so if you have 3 values separated by colons, the middle one here represents the step size. If you wanted to do decreasing order, you can just put them backwards. Oh, sorry. And then do -1 as your step size. So 5, 4, 3, 2, 1. There's an alternative way to specify this, which is the word range. It's a function range. So start, stop, and then you can specify length 100, for example. Would be a way to do that. So range is much more flexible. And if you like want to remember how to look at it, you just type $range, and it'll tell you all the methods attached to it. Okay, so we have a choice to make here as a class, which is I have a project kind of set up at the end, which is built for us to kind of like implement some like fun OLS type stuff. It might be a little hard because we haven't gotten to like some of the fun bits, but I think people here are like reasonably good at have maybe rolled their own like least squares estimator. So we can jump to that and I can just let you guys tinker around and we can kind of play, or I can kind of continue with like the lecture as it currently is, and we can try and get through as much like lecture type content as you want. So I don't know if people have strong opinions about which one they would prefer, like if people are like want to tinker on their own, or if they want more lecture type stuff.
For the project, are there any sort of like checkpointy type pieces in it?
Yeah, there's a couple. Like, so for example, so basically this is the project that I'll show people. So we're basically just bootstrapping beta estimates, and I give you the linear algebra stuff. I'll show you how to do the linear algebra. And I'll show you the math. And I'm basically giving you code to start with, and then I would also give you kind of the core OLS stuff, which was going to be a concept check, but I don't know. Or we can just take a break and roll through. Oh yeah, the slide deck will be up on the GitHub repo. So I'll post that available. So I don't know, does anybody have strong feelings about which one they want to do? Because if not, I think I may end up just lecturing a little more because I just kind of want to get through basic stuff. And I can defer this to something else and we can make it like crazy fun and a little more performant. Because right now it'll end up being dumb. Yeah, I agree. Part of this project is like a dispatching thing, but we can do it without dispatching just as well, I think. Prefer lecture. Does anyone extremely prefer the project? If you want to do it on the side, then I can help you out. Okay, I'm just going to do the lecture. Does that sound good? Why don't we take a break until 12:10, and then we'll come back and I'll use the last 50 for a lecture. Does that sound good? Okay, perfect. Let's do it. All right, I'll see everyone back here at 12. We're back at the top of the break. Thank you very much to the wonderful Stanford GSB events team. They were like kind of fantastic. It's amazing. Okay. All right, so I'm gonna turn off my like starstruckedness. But geez, fantastic people. Okay. All right, so we're agreed we're going to do kind of the lecture is just going to be kind of the last little bit. And if you want to, I actually have. I'll go to the repository. So there's a GitHub repository that I'm posting in the chat. And this has all the code in it that we've written here today. So if you want to go and try the project, if you go to session 1, the instructions are at the end of intro.ipy notebook. So if you scroll to the end, you'll be able to get to the end of the lecture notes. And if you want to see my answer to just the basic version of the project, if you go to project.jl, you will see how it is that I've implemented this bootstrapped standard error estimator. Hopefully, if you're like super into like solving this kind of stuff, it's there for you. And you can also ask me questions about it as needed. Okay. And I'll also post the recordings up on that same repository so you can access them if you need to. Okay, so we just kind of went through the for loop here. For loops go through whatever you want to. The alternative here is a while loop, which says keep going until the thing here is false. This is another common construct you may be aware of in other languages. It's not that common, I find, to work in with like data stuff. But basically this will run, we're going to set x equal to 100. We're going to check to make sure x is greater than 1. If it's greater than 1, then we run the code in here and go again. So in this case, it's going to print out whatever x is. It's going to take x and divide it by 2. The alternative for this, you can write in shorthand, is divide by equal to, which these two are equivalent. And so what's going to happen is it'll keep dividing it by 2 until it becomes less than 1. Okay. And the last x here is not printed out because this was evaluated false. So it stopped when it saw that x was 0.78. So while loops are, I have some thoughts on them basically, but because we're not writing like web servers or whatever, typically, it's kind of rare to use while loops. But in research computing, there is kind of a use case where they're very useful, right? So I think if you're working on something that is convergence related, right? If you're doing some kind of conditional evaluation, you're searching for something. While loops are a very, very good tool for trying to like get within some epsilon of an answer. Because for loops can't help you there, because for loops require you to know a priori how long your loop is going to run. Not necessarily for some iterables that are, not finitely defined, but while loops are much more resilient to that particular thought process, right? So for example, you might be looking for some value such that some loss function of that value is less than or equal to epsilon. And so this is a very good use case for working with that. So if you're the kind of person, maybe you do like some like DLP type stuff, like this is kind of a good fit because you kind of want to evaluate until convergence. So just keep that in your toolkit. You may also be aware of break and continue. So in R, I believe this is called, continue is called next. I think break is common along a lot of languages. Break just says, if you get to me, if you see the word break, exit the current loop. I'm done. This loop is over now. We're not going to do any further evaluation of this loop. Just exit it and go on. So for example, in this case, we're going to go through 1 to 10. It's going to print whatever I is, and then it's going to break, which means stop this loop. At that point, it's going to go to outside of the loop and hit print line all done. So we'll see it's only going to print 1 because it printed this, even though it had 2 through 10 to go. It just saw break and it exited early. So this is a good way if you're like in a while loop, for example, if you've hit some absolute failure condition, right? So for example, if you're like, okay, there's no way I can solve this particular use case, I can just do break and move on with my life because I don't need to waste time just spinning my wheels. It's also good to have a break inside of a while loop if you know that it's possible that you could end up in an infinite loop. So break is a good tool for you to like think about not getting stuck spinning out doing compute that doesn't matter. Okay. Continue is less aggressive. Continue just says the current iteration is bad. I don't want this one. I'm done with it, or I just don't need to do anything else. I can just go to the next one. So for example, here I'm going for I in 1 through 10. So this will be 1, then 2, then 3, so on. And then I'm going to check the remainder. So if the remainder is 0 with 2, which means that it is an even number, I'm just going to hit continue. If it's not an even number, it's going to skip past this and it's going to go to the print statement. So it'll print out basically only odd numbers. So when it hits the continue here, it's just going to terminate this I is equal to whatever the even number is and just exit, go to the next iteration. So this can be very handy as well if you like are going through your for loop and you hit something where you're like, okay, either I know the answer early to something, I can just like assign it. I don't have to keep doing math. I can kind of like back out of my loop very quickly. So it's kind of a good fit for that particular use case. I had a boss who got really mad at me for using this when I was like a software engineer. And he would call me up after I submitted code, be like, why would you use break and continue? Like, this is like, don't do this. Because it makes it really hard to read. And he's right, because when you see break and like, sometimes you can't see break and continue. They are not as obvious to your eye as our if statements, for example. So if you miss them, it's really hard to read and you can end up with kind of some weird behavior that you didn't expect. So kind of use them sparingly. But if you have an annoyingly correct boss or you care about your style, consider just use conditional evaluation. So I've rewritten the above to just ignore, like I don't have to use continue here. I just have an if statement, I check, and if it's not even, I print it. Otherwise, I just skip. And because there's nothing else at the end of this loop, I'm done. So if and else are really, really good for that kind of thing. So, be cautious with them. Exceptions. I debated a really long time about whether or not I was going to talk about exceptions at all. Because my belief is that if you are using try, catch, finally, any of that stuff, you're writing terrible code. I don't know that that's super true, but it's what I feel like. If you're catching exceptions, you're just kind of like not checking things correctly. But in the event that you are a person who is like a suitably advanced programmer that you can use try, catch, and finally responsibly, I wanted to show you the syntax at the very least. So it's pretty common, like in other languages. Try says try to do this thing and move on if it gets done. If you have an error of any kind, catch, and you can optionally define a variable that you want to assign the exception to. In this case, it's E. I can print out the error. And then finally says, whether I got a try or a catch, do this thing. So finally is like a good way if you're like reading a big file, you can like close the buffer or do anything like that. So if I run this, because hats are a dog's best friend is not a real function, I haven't defined it, it'll exit out of the try block, it'll go into the catch block, it'll assign this undef var error to E. I'm printing it out and you'll see I'm getting this undef var error in my my output. And then finally it's going to print I did the work, boss. Okay. So I'm not going to go into this a whole lot more for right now, just because like, just be careful with try catch. Because if you don't pay attention, so Alex has a good note here, which is like, it's really good for handling data, because when you handle data, like big streams of data, you're not quite sure what it is that you're going to get. So try catch can be good. So I understand, I am sympathetic to that. But if you're doing like numerics and numerical computation, chances are really good that your try catch, if you ignore good errors that are like method errors or undefined variable errors, you're going to spend a lot of time spinning your brain out trying to understand why your code's not running, just because you're throwing away exceptions. So like sometimes you really want to see an error, but that is a good point. If you're doing like data IO, that's a pretty good one. I buy that. Okay. Okay, any questions on any of the control flow stuff? I think it's like pretty basic. Okay. All right, linear algebra. This is everyone's favorite topic. We all love eigenvalues. That's going to be my next tattoo. Is an eigenvalue, I'm sure. I'm very committed to that. And Julia has a really, really, really good way of handling linear algebra, right? So it talks to BLAS and LAPACK, and you can swap it out with like MKL if you want like a bunch of free speed, and you have Intel processors. Like you can do all kinds of cool stuff with linear algebra, and it's amazingly fast. So everything that one guy in the 1970s wrote in Fortran, you can reach, and it goes really well. Okay. So I'm just going to give you, so first, if anytime you're going to use any kind of linear algebra stuff, just using linear algebra. So for example, if I'm in the REPL, you want to call using linear algebra. And this will give you access to the full suite of linear algebra functions. Okay. And linear algebra comes with a ton of functions, like I do not understand. I imagine this is like Gil Strang would be like very excited with this kind of stuff, I'm sure, because he loves those kinds of things. But inversions is inv, det, determinant, tr is trace, so on and so forth. A lot of these are probably fairly similar to the MATLAB versions, because Julia was kind of made by a bunch of people who hated MATLAB, but still kind of like the linear algebra calls. So eigvals and eigvex, or eigen, also gets you both together. Factorize is like a good way of like, factorize is an awesome function actually, because, and I didn't know about this one before I made these slides, but it'll look at your vector and it'll be like, could this be sparse? If it's sparse, then I'll give it a sparse representation. It'll save you a bunch of memory. If it's something that you can like make into a triangular or something like that, it'll make it a triangular and save you a bunch of memory. So it has a lot of cool, like, and you can also specify an explicit factorization if you want to. You're like, no, I'm going to make this diagonal, and it'll do that for you. So factorize is really, really beautiful. If you really want to get into like the linear algebra suite, you can go check out the docs. And you can even like tinker around with like the BLAS and LAPACK low level stuff, but you probably shouldn't be doing that, just because, you know, if you're doing that, it should be kind of at the language level, and somebody should fix it if it's not working for you. Okay, so basically all the linear algebra stuff you could ever want. So I think this is like the first time I actually get to like some statistics here, but I imagine most people here have gone through some kind of like statistics training, or at least that's my hope. Otherwise, this is going to be very boring. So like, I'm just going to consider this like super basic specification, which is just y is equal to x beta plus epsilon, right? So just some error term and some coefficients, and I'm assuming that x here has a column of ones, right? That's our constant term. Well, it doesn't have to, but I'm assuming it is anyway. So we know that the least squares estimate of this is just beta hat is equal to x prime x inverse x prime y, right? Everybody can say that a million times in their sleep, I'm sure. If you've done like your first year PhD in econ, that's like fried into your brain. At least it is in mine. So we can work with these normal equations, and you know, it'll hopefully give us a little bit of a tour of some of the linear algebra stuff, so we know how to work with it. Okay, so here I'm going to import linear algebra. That's a necessary if we want to work with matrix inverse. I'm going to create a vector, a matrix called X, that's going to have 100 rows and 3 columns. And I'm just getting standard Gaussian. So rand n here gives me 100 by 3 array. And then I'm going to change the first column to just be ones, because I'm going to set these to be the constant. So I have intercept term and then 2 just kind of random X terms in columns. Okay. And then I'm going to define beta. I'll put this in the chat in case people want to copy it and play around with it. I'm going to define beta here. So this is going to be my intercept term. 2 is going to be my weighting on column 2, and then negative 1.5 is the coefficient for column 3. And then I'm just going to create some random y's, right? So, or not y's, random y's, but x times b, that gives me the actual like projection. And then I'm going to add some Gaussian noise on top of it. So these are just the epsilons. These are just normal epsilons. So you get a bunch of stuff that comes with like having IID errors and all that stuff. Okay, so this is nice and easy. Nothing here should look too crazy. Any questions on this?
Just I was surprised that like multiplication was immediately matrix multiplication. I feel like in Python I had to like jump through hoops.
Yes.
Is there like a broadcasted version of multiplication that I need to be worried about as well?
Yes. So if you do x dot times.
Okay.
So for example, let's see actually if that gives me an error. Yeah. So if I do x, is that right? Yeah. So if I do this, so if I take the transpose of beta and I make it a row vector, because I had, and it's of length, it's width 3, and the other thing is width 3. What it'll do is replicate beta and multiply it by every dot piece, element-wise multiplication. So at the end of this term here, let me actually put this at the end so we can see what it looks like. This will actually give me 5 times, this will actually do the element-wise multiplication. So dot times is a really good way to do that as well. If you want to broadcast arrays in the same way that you might with R, because R does this like broadcasting up and down stuff for free. Was there another question?
So these vectors are always interpreted as column vectors, right? So the beta, for instance, here.
Yeah. So they're
because you didn't specify that it's a column vector or something, right?
So it's specified as you can make it. So for example, if I do this makes it a row vector explicitly. Because,
I see.
Or if you wanted to make it a column vector explicitly, this actually makes it a 3x1 array. This is actually doesn't have a second dimension. It only has just length. This one, both of these have length and width.
But then in the multiplication, it's interpreted as a column vector, right? Of 3 times 1.
Yeah, it'll go for column vector by default, which is kind of why I had to do this part here with the transpose.
Right.
Good eye. That's a good one. Okay. Okay. Was there another question? Was that good? All right. So, like, we can square matrices very easily, right? So x prime says transpose x. I believe you can also do transpose explicitly as a function. This should give you the same thing. But the nice thing about using this, using the apostrophe here to transpose, means that you don't actually have to put the multiplication there. It just says I have an adjoint, which is this x prime here, and it's right next to another matrix. So I'm just going to multiply them together. So this will actually square the matrix for you very easily. Okay, so that's, if you want to do that. This is also technically correct. This should give you the same answer. But to my eye, I like the x prime x, so I'm going to keep it in. All right, so beta hat here, I'm just going to define the entire specification here. These are the normal equations. So I'm just going to do x prime x inverse, and I'm going to multiply that by x prime y, and that gets me beta hat, which, as we can see, is pretty close to our, it's like 5, 2, and negative 1.5, right? That's about what we'd expect. And if I wanted to make predictions using beta hat, I'm just going to do x times beta hat. And this will give me all of my predicted quantities for y. And then I can calculate the error between y hat and y. So this is a big vector, big long vector of the difference of the prediction error. And then I can just calculate this, the squared standard error, which I think actually this should be divided by like n minus k. But at the very least, I'm just going to square the error, and we'll worry about the divisor and the quotient in just a second. So this gives me my squared error.
So does the MATLAB shortcut also work? That would be x, I think /y, and that should give you immediately the beta.
Yes, I believe so. That's the linear solve, right? X.
Right.
Is that right? Yes, and it's a backslash in this case.
Right.
Yeah. So that'll also give you the linear solve as well. Good reminder. I appreciate it. I wanted to mention that and I forgot. Thank you. Okay. So any questions about what I've done here so far? Okay. I don't know if we want to do this one. Do you guys want to try to roll like the basic version of this with the spherical errors? Or is that like something we've done enough of in like first year PhD world? I don't know. Let's see. What do I have next here? No, I'm going to skip this one because I want to get to the type system because I think it's important. Okay, so I'll leave this one up. This one should be like reasonably easy to do. I've given you all the information that you have for like, spherical standard errors if you want to implement them as well. And this is kind of like the first half of the project, basically, without any complexity. Okay. Any questions on like the linear algebra stuff before I move on from it? Like it should be reasonably explanatory as you need. Okay. Cool. So with that, I'm going to move into types.
Maybe just one short question. So regarding the inverse, how it works if there's stuff like collinear and so on.
It'll try. It'll basically say like,
and then it will resort automatically to some sort of Penrose inverse or something if it's very close to collinear.
It does whatever LAPACK does. So or BLAS, right? It'll try to do the inverse.
Okay.
But I don't know if it gives you like some kind of like magic collinear matrix inverse. But you will get an exception if it's not singular. So if you try to invert something that's not singular, it'll give you an error. It'll get mad.
Okay.
But I don't know how about like close. Yeah. And it doesn't do left. It doesn't natively do left or right inverses. So I think it assumes a square. So if you need a left or right inverse, you may have to like do a little bit of work to figure that out. There may be a shortcut function, but I don't remember what it is. Okay, that was a good question. Other ones?
Is there a way to bind arrays together?
Yes. Here, let me give you the example of this. So they are called hcat and vcat. So I'm going to call this M1 is equal to rand 5, 10. Right? So 5 rows, 10 columns. Actually, here, let me make this smaller. 2 and 3. And then M2 is equal to rand 2 and 5. Okay. So if I wanted to smush these together, I can do hcat M1, M2, which gives me a 2 by 8. This lines them up. So it takes M1 and then it smushes M2 right next to it. If, for example, I had, like let's say I have M3, which is 10 rows and 3 columns to be conformable with M1, I can do vcat, which is M1, M3, and that'll smush them on top of each other. I believe there's also shorthand that people may be familiar with for the in MATLAB. So you can do, I think, is it M1, M2? Yeah. So if you just do brackets and put a space next to them, it'll do the concatenation for you. And I believe you can also put a semicolon in here and do M1, M3 as well. Yeah. So so you can concatenate them by kind of declaring like a block matrix with traditional Julia syntax. Okay, so I hope that helps. All right, other questions? These are good. You guys got amped for the linear algebra. I love it. Okay. Man, you guys really are nerds. Jesus. Okay. So like Julia does not have objects necessarily in the same way that they might in like R, Python, or like lots of languages have kind of objects. Julia has instantiated types, and I think the difference between instantiated types and objects is kind of meaningless. Like they do like objecty stuff, if you're familiar with that. But people kind of get mad when you talk about like Julia being object oriented. I don't know why. Some people are grumpy about that. But basically everything is heavily typed. And the type system in Julia is a work of art. It's like a really beautiful thing. And it makes so many things just work. And if you're like writing code that just kind of goes, you don't need to think about it ever. But it's just wondrously beautiful. And I have so much fun with it. But basically, everything in Julia has a type. It has to have a type. And every type could be a subtype of another type. So you can have all these ladders of types. And so for example, here, I actually have this code here. You'll note that I have this less than colon symbol, which basically means return true if left is a subtype of right. So for example, here, I have the Julia top level type. So there is one type in Julia that everything else is descended from, which is called any. So any means anything that you could possibly find. All things are subtypes of any. Int64 has a very long type chain, which is int64, because there is also int8, int16, int32, int128. And it says that it's signed because we care about the negative numbers. These are all subtypes of integers, which are subtypes of real, which are subtypes of numbers, which are subtypes of any, right? So if I run this, I will get true because all of this is true. Everything is a subtype of any, okay? So when you're working in things, remember that every type that you have has a lot of parent nodes that determine its behavior. And when we write functions that handle different types, we can inject functions at different levels in this type chain. So for example, you might have a function that you know has to be accept a number. I don't want a string. I just want at least a number. And your function should be able to work with, will be able to work with real, integer, signed, int64, float64, floating point, so on and so forth. So you can look at these type systems and be like, oh, okay, I want kind of the most general one that allows me to do stuff. So this is important for writing big kind of high performance functions, is like being aware of types. Because the number one thing that slows you down in Julia is the compiler being unable to infer the type of a function, the output of a function. And when that happens, you run into some serious problems with slowness. Okay. So you will often see colon with a variable name on the left and a type name on the right. So this is how you tell Julia, I expect the thing on the left to be of type thing on the right. So for example, if I do this, howdy colon string, right? We know that this is a string. This will actually just give me string, right? It doesn't do anything else. Julia is automatically kind of adding these annotations as it goes along, so it knows what things are. But if I do this, I'm going to get an error, right? And the reason is when I see the 1, there's no decimal point there, so it's an integer. But I have colon float64 afterward. And so it says, no, error in type assert, expected float64, got value of int64. So you will see this error a lot in Julia when you start out, and it's going to suck because you're not going to know what's going on. But if you see this error, it's because at some point, it expected to receive a different type than it got. Okay, that's all it is. And I can broaden this out to use real instead, right? Real is a super type. It's actually a very high level super type that's very permissive about what's allowed underneath it. So if I run this, it'll just give me 1 because 1's int64 also happens to be real. This is true, right? It is a real, but it also happens to be an int64. Okay. Questions about the type annotation so far? Because this can be a little weird for people.
So if I have, for instance, this 1, how can I get all the super types of 1? So basically,
okay.
How do I go backwards in the type hierarchy?
So if I go type of 1, this will return me type int64.
Mm-hmm.
And if I add, you'll note if I actually here, I'll assign this type to a variable. And then I can go TT and then I hit dot. So the dot is how we access properties for various things. And it'll give me a bunch of options if I hit tab inside of here. But if I type dot super, it'll give me the super type of int64. And if I type dot super for that, it'll give me integer. Dot super for that, it'll give me real, so on and so forth.
Oh, that's cool.
And you can write a function that'll like unwrap this chain if you want to. It's pretty quick, but that's like how you would get to the type very quickly if you wanted to figure out what it's a type of. And you'll be able to see them inside of the REPL. So if you're working in the REPL, you can be like, you can type in a type that you're aware of, and it'll tell you what the super is usually in the documentation string. Okay. Alrighty. Okay, so we got like 20 minutes. Okay, so type annotations show up in two places correctly. So this thing that I've done right here is weird. Nobody does this, right? You don't just like annotate values, especially constant values like this, which it's just really weird. People don't quite like it. Sometimes people try to do it as like a hint to the compiler. The compiler is probably smarter than you, so like just don't do that. And it's a really good way to break your code, because you don't want to be too strict with your typing. You want it to be allowed to flow and to be different, especially if you're working with automatic differentiation, because those types change underneath you. So in the two correct ways that they show up is in the argument types. This is the most common by far. This is saying, I have created a function f that's different from all other f functions, that accepts an integer in the first spot and a float 64 in the second spot. And this function will work if you give me an integer and then a float 64. Okay. The other way that it is commonly used is at the end of the return value. This is intended to say, I know what the output of this is. And sometimes that can help Julia infer the return value. But again, I think it's just kind of a waste of time. Like I wouldn't do this. This is the only time I use type annotations really. Also in parametric typing, but that's a discussion for later. So keep type annotations to a minimum, unless it's important for dispatching on your function. I'll talk a little bit about dispatch, hopefully. Okay. So the core atom of Julia's type system is called an abstract type. An abstract type is a thing that you can't make. It doesn't exist. It's just an idea. It's an organizing concept to say type A is the parent of type B. That's it. That's all it does. You cannot create type A. You can't make it. You can't pass it around. You can't put values in it, any of that stuff. So integer, for example, no, not int, integer, the full word, it's a much bigger super type, telling us that whatever subtype we get, it does all the things that integers do. It doesn't have a floating point. It could be negative, could be positive. It has some bit allocation, but it does integer stuff. And so it's a valuable heuristic tool for organizing all the types that fall under it that have more applied properties. So I'm gonna show you a bit of an example on how to do this. But first I want to talk about structs. So structs are the other thing that can be instantiated. If you come from like Python world or whatever, these are objects, not classes. So classes you can think of as abstract types, even though it's a little frivolous, but structs are objects. So structs are also called composite types or records, things like that. If you come from like, I don't know, F# uses records. Here's an example of how we might define a struct with no super type. So for example, I'm creating struct some stuff is the name of this struct, and then I have some field inside of it, and I'm saying that whatever I'm going to put in here is a float 64. So and down here I'm actually creating it. Note that I'm calling some stuff like I would a function, but I'm giving it a value of 0.5, and it's going to assign 0.5 to field. Okay, so when I run this, I'm going to get a value. You'll see it's kind of printing it out weird because it doesn't know how to print out this new type in a pretty way. But I can access that field with 0.5, with some stuff dot name of the field.
Question for you in the chat.
Oh, thank you, thank you. Difference between tuples and structs. Structs are more rigorous in that they, you can change the type system. So you predefine a structure of things that you're going to put into it, and you have the additional benefit that you say, like, I'm not just going to accept a tuple into my function. I'm going to accept a some stuff, and I know there's all this special stuff about some stuff. Like I know it's going to have field. I always know it's going to have a value in field. With tuples, like you don't have that guarantee. You don't know like a priori what the size is, all kinds of different things. But you can also make them mutable. So if you type mutable struct, you can change them just like you would. So they can kind of be like mutable structs if you really wanted to. Some people, there's a lot of people in Julia who are like, I don't care about mutable structs. Like they're fine. I like them. I use them sometimes. At least in the Turing world, we've been trying to get away from mutability and just kind of work with like immutable structs. But that's a user preference type thing. But yeah, the big difference is we can tell you what type subtype is of, we can tell you everything we need to know about a struct, but we can't tell you everything you need to know about a tuple. Okay. So let me show you how we can combine structs, which are things that we can make, and abstract types, which we can't make. And so I'm going to wrap these in a module, and modules are the things that I think I've had like 2 questions on about namespace management. So when we have a module, we keep everything inside of the named module, and we have to access it by name or export it. It just kind of keeps everything locked up in a little box so that it doesn't clutter up our namespace if we don't have it. Okay. All right. So I'm going to give you a little example of this like module system of this module I've written here. So I'm going to create something called module vehicle types. And so all I'm doing is declaring a name of a thing that's like linear algebra, right? Linear algebra is a module. In this case, I'm creating a new module that is called vehicle types. I'm going to define a top level type called mobility device. And mobility device is like anything that is designed to help you move around. It's a very, very general thing. I'm going to give you subtypes for car and bicycle. Note that these are still abstract types because I'm going to go a little further. So abstract type for car is a mobility device. That's why I'm subtyping it using this less than colon. Same thing for bicycle. Bicycle less than colon mobility device. And now I have car and bicycle in the tree, the type tree. Then I'm going to give you some subtypes for car. So I have combustion cars, which have, I've defined like 2 properties here, which is gallons, which is how many gallons you can put in a tank, and the miles per gallon, right? So and both of these I'm saying are float 64. And then I'm giving you an electric car that says electric miles, right? So how far can this car go on a full charge? Approximately is how I would do this. Both of these are subtypes of car. And then I have for bicycles, I have road bikes and mountain bikes. And road bikes are defined by their purchase cost. Mountain bikes are defined by their maintenance cost. If you're a really cheap, crappy mountain bike, you only pay maintenance. And then I'm going to do the exports. These are the things that I want to be accessible outside of the namespace. In this case, I'm actually exporting pretty much everything I define in here because I want to be able to use it later. But this is a little module here. If you see this replacing module vehicle types, it's because I pre-ran this code, so it's like overwriting the module I wrote before. And now you'll see I have main.vehicle types to access. So I'm going to import all of the types that I just wrote. So when I call using main vehicle types, it's going to say, oh, you're conflicting with an existing modifier. This is only because I'm doing this in a notebook. You won't see this if you do this correctly in like actual code. And now I'm going to make some of these structs, right? So I have electric, combustion, road, and mountain. These are the structs that I defined that are not abstract types. So these 4 are structs, which means we can put stuff in them and assign values to maintenance cost, purchase cost, e-miles, etc. Okay. So I'm just going to make some of these and I'll assign them to variables. So here I'm saying this electric car has 225 e-miles. This combustion car has an 11-gallon tank with 21 miles to the gallon. This road bike costs $1,501. And then this mountain bike costs $50 or $50 to maintain. Okay. Okay. So all of these are structs I've created and I've assigned them values. Okay. So now I'm going to do some function stuff, right? So I'm going to show you how to think about the type system here. So I'm going to define a function with two signatures. So the thing that makes it have two signatures is that the name is the same. Both of these function names are move. And it's going to accept one argument. And I've added a type annotation to only the first one. The second one, there is no type annotation. When you don't include a type annotation, it sets it to any by default. But the convention is not to write any, because then we'd have to write any a whole bunch. So we just kind of leave it off. So what happens is, actually here, let me do a single call here. What's going to happen when I call this? Well, it's going to look at the type of the thing that I've given it, which is electric, which is a subtype of car, which is a subtype of mobility device. And Julia's compiler always tries to find the tightest type constraint, the smallest type constraint, to dispatch this struct that I have to a function. And in this case, the tightest one is mobility device, because mobility device is a subtype of any, which is a smaller type than is this one, which is any. So when I run this, it'll run true, because electric car is a mobility device. Okay. So if instead I give it a different, if I give it a different type, which is a string, which I haven't defined at all, it'll see, is this thing a mobility device? And it'll say, no, it's not. So it'll go to this one here and it'll print out false. Okay. So that's just like really nice. I've written two functions and I've expressed all the behavior for every possible type that exists in Julia right now. So if I can do this map call and I do it across the thing, I get, hey, all of these things move except for hats. Questions about this?
Yes. I have a question about. Oh.
Hit me.
You go ahead.
Okay. I have a question about the way we refer to these things. Capital E electric, we call that a struct. The lowercase electric car, do we also call that a struct, or is that an instance of a struct, or how should we refer to it?
Yeah, so electric car, electric underscore car, that one's a variable name, right? So the thing that's inside of that is an instantiated type or an instance. If you want to get kind of like, yeah, I think that would be what people would call it. An instance is probably the correct, like the technically correct term for it. Okay, yes.
Thanks.
Alex.
So initially when you wrote moves and said that it would take a thing of any type, my intuition is that this would somehow overwrite the initial moves function, because now you're saying, like, whenever you give it anything, return false. It's a little weird to think of the first you define this very specific thing, then you define this general thing that does not alter the specific thing that you already asserted.
Yes. So that's the main. So if you were to like cook up a table of the things that make Julia really different from everything else, it is this. This is called multiple dispatch. And it is the most magic thing here, which is I can continue to add more signatures to this. There are functions in Julia that have like hundreds of signatures. There's ones for like int and float, int and int, float 64 and float 8, float 8 and float 32, right? Like they have all of these little mixtures of things, and that makes it just kind of go. And they're not exclusive in any way. Like you can even think of them as like, they're just really fluid. Like it's perfectly fine for all of these to exist next to one another without modifying each other. There's no overloading. You're just kind of like tacking these on to the end of the list of things that's available to the compiler.
And it tries to match it with the most specific possible one at all times.
Yeah. So if I do something like moves thing car, right, which is a more specific type, equals, hell yeah, homie, right? If I did this, then it'll return a different thing. So here, let me actually go back. So this will be a weird call, right? So the first two, these are cars. So when it runs across these function, it says, hell yeah, homie. And fast bike and cool bike, because I don't have a specific version for this, they go up the next level and they say, okay, mobility device. Is there a function that calls mobility device? That's tighter than any, which is this one. So it'll give me true. So it always tries to constrict. And this works with as many variables as you have typed.
That part feels especially brain twisting because like you might have like two variables, one matches very tightly and the other one only matches a very loose version. So how do I know which of the function definitions I'm going to arrive at?
That's an art. So it takes a really long time to do that. But when you're in doubt, just try and make your function, your methods as tight as possible. Like and then you can loosen them up later as you go along. And just like forcing something to be really tight helps. But Julia will also give you a warning. It'll say it'll give you an error that says method ambiguous. Please define this. And it'll give you a correction to say, if you add this type constraint, then it'll dispatch to this method. It'll tell you which line number it thinks it will go to. So it tries to help you out with like the art of writing good Julia. Okay.
And just to be clear,
go ahead.
The pattern of multiple dispatching doesn't depend on the order you wrote those 3 lines, right? Like if you had moves thing equals false as the first line, it would also be the same thing.
Correct. Doesn't care. Yep. Okay. I'll skip these other ones because these are just like more examples of like specificity and things like that.
Quick question in the chat.
Oh, thank you. Thank you. Are the type structures branching? Yes, they can be. So you can dump out of a tree very early and go straight to a struct. And then you can have the other branch in a node just like continue to whittle its way down in abstract types. So you can basically step off anywhere you want in the type system. And Julia still has a really good job, does a really good job of dispatching on your type tree. So you can get off the station at any point you want. That's a good question. Okay, I think I need to start wrapping up, but this is multiple dispatch. So we defined a hierarchy of types. We defined functions on those types. So anytime you work in Julia, this is all happening behind the scenes. There's a bunch of nerds who really like multiple dispatch, and they're writing these elaborate type systems that make everything just work for you. And that's kind of the beauty of the language that you don't see quite so much if you're a user. But it makes it really, really joyful to write good Julia code. So I think, damn, see, I didn't get to data IO, but it's there. Okay, so I think we have to wrap up, but I will be here if people have like questions for the addition, like, want to hang out for a bit. Thank you guys for hanging out with me for a couple hours. I appreciated it. You guys have good questions. You're like smart people. I dig it. Okay.